Right now, you're hurtling through space at a speed that should terrify you, yet you feel perfectly still. Earth spins, the planet orbits, the sun races, the galaxy drifts, and the universe expands under your feet all at once. So why doesn't your body notice, and what, if anything, can we truly say we're moving relative to? Stillness is not a fact of nature. It is a story your nervous system tells to keep you alive. And that story begins to fail the moment you ask what counts as at rest. Look closely at an ordinary room, and you'll find the first clue. Your body is a detector of change, not of speed. It notices jolts, tilts, and strain, yet it grows quiet when motion is smooth, shared, and unopposed. The floor, the air, your bones, and even your eyes cooperate, subtracting what stays constant until here feels fixed. That biological bargain is powerful, but it comes with a cost, because the universe does not grant stillness as a universal right. To physics, rest is a relationship, not a location. Choose a different frame and the same moment redraws itself, as if the cosmos had rotated the map beneath you. So we will do what your senses cannot. We will compare clocks to stars, pendulums to horizons, and microscopic temperature patterns to the deepest sky. Each comparison is a confession, an admission that motion becomes visible only when something else refuses to move with you. In this film, we follow those refusals, not as metaphors but as measurements, the kind that survive doubt, calibration, and the stubborn noise of reality. We begin where certainty feels strongest, in the calm logic of balance and the quiet confidence of a steady gaze. Then we introduce a single mismatch, small enough to ignore until it becomes impossible to unsee. From there, the scales widen. We move from familiar mechanics to celestial geometry, from local patterns in air and water to the long bookkeeping of starlight. And as the layers stack, a stranger tension emerges. Relativity denies a final, privileged stillness, yet the cosmos offers a practical baseline that tempts us to call it home. That temptation is where the mystery deepens, because a baseline is not an anchor, and a reference is not a resting place. By the time we reach the farthest frame we can operationally define, the question is no longer how fast, but relative to what, and what that question can never finally settle. This is an investigation into speed, yes, but also into perception, evidence, and the limits of what any observer can claim. The terrifying reality is not that motion surrounds you, it is that stillness was always conditional, negotiated, and profoundly incomplete. If you want to understand what you're truly doing in space, you must learn to distrust comfort, and to listen instead for the thin residual signals that comfort was designed to erase. Because out there, the universe is not waiting. It is moving, quietly, relentlessly, and it will not provide a final place to stand. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We'll peel back motion one scale at a time, from the tricks of the inner ear to the evidence written into sky, light, and cosmic background. And when our best frame of rest appears, we'll test what it can explain and what it cannot. Sit in a chair and everything agrees you are at rest. Your muscles soften, your eyes settle, and the room feels nailed down, as if the air itself has stopped negotiating. Stillness feels like a fact, not a guess, because your senses report no urgent change. Physics does not share that feeling. Motion is not something you need to notice for it to be real, and the universe keeps its accounts whether your nerves file a report or not. In physics, at rest is never a sensation. It is a relationship stated with respect to something else. The first puzzle is personal. If we are moving, why do we feel nothing, and why does the mind treat calm as proof? The second puzzle is cosmic. If motion is relative, what does it mean to move through space? And who gets to decide what through even refers to? Your body is built to detect changes, not steady states, because change is what once signaled danger. You feel acceleration more than constant velocity because acceleration threatens balance, posture, and survival. Constant speed, by itself, rarely does. A smooth ride can be fast, yet feel like nothing, because the forces on you barely change. Inside your inner ear, the vestibular system tracks rotation and linear acceleration with remarkable sensitivity, Tiny fluid-filled semicircular canals detect angular acceleration, while otolith organs sense linear acceleration and tilt through microscopic crystals that tug on hair cells. When motion changes, those hair cells bend and fire, sending a clear message that something is happening. When motion stays constant, the signal fades into baseline. The fluids settle, the hair cells return toward equilibrium, and the brain stops treating the stimulus as news. This fading is not a flaw. It is a filter that prevents constant stimulation from drowning out new danger, and it keeps attention available for the next unexpected shove. Your brain subtracts what does not change, then calls the remainder reality. That subtraction happens everywhere in perception: hearing, touch, even smell, because a nervous system that reported every steady detail would be too busy to react. The cost is philosophical. Stability can be a manufactured impression, not an objective verdict. This is why a plane at cruising speed can feel still. You share the motion with the cabin, the air and the seat, and the vibrations that would betray speed are engineered away. With no shifting forces, your body has little to report, so the mind quietly labels the situation rest. Motion becomes invisible when it is smooth and shared by everything around you. If you and your reference objects move together, there is no local clue, and the world looks stable because your frame is stable. The trick is not that motion disappears. The trick is that evidence of motion is often differential, not absolute. Even your eyes are easily fooled. Vision infers motion from relative change across the retina, and the brain stabilizes the scene by subtracting your own eye movements. If the whole scene moves with you, the scene does not slide, and your visual system has nothing obvious to compare. So the documentary begins with a reversal. The feeling of stillness is not evidence of rest. It is evidence that your motion is steady and your environment is moving with you, like a stage set carried by a hidden conveyor. The calm is real, but it is not the same as immobility. Now widen the scale without leaving the room. Your chair sits on a floor, on a crust, on a spinning planet, and that spin is the first mechanical layer beneath your feet. In a quiet interior, the motion is invisible, yet outside the walls the planet is sweeping a vast circle through space. Earth rotates once in about 24 hours, more precisely in a sidereal day of about 23 hours, 56 minutes. That small difference matters because the stars, not the sun, define the true rotation against deep space. At the equator, that rotation carries you around at roughly 465 meters per second, a speed set by Earth's radius and its angular rate. That is about 1,670 kilometers per hour. In visual terms, imagine a point on the equator tracing a circle nearly 40,000 kilometers around, every day, without pausing. The surface feels solid, but the geometry is relentless. Radius times rotation becomes speed, whether you notice it or not. Compare that to sound in air at sea level, about 343 meters per second under typical conditions. Sound speed shifts with temperature, humidity, and pressure, but the number is a useful anchor for intuition. Without any engine, you're already moving faster than typical sound speed, and you're doing it while sitting still. This is not a trick of units. It is a reminder that speed can be huge and still feel like nothing, provided it is steady and shared. Constant velocity hides when acceleration is small, and when the surrounding world, air, walls, furniture, moves in lockstep. Earth's rotation does produce acceleration, but it is gentle. The centripetal acceleration at the equator is about 0.034 meters per second squared, and that is only around 0.003 of gravity. Gravity overwhelms it so completely that your inner ear treats it as background, not as an emergency. You can even see its fingerprint in your weight. Because rotation slightly reduces effective gravity at the equator, you weigh a little less there than near the poles, where the rotational effect is smaller. The difference is subtle, but it is measurable, and it reminds us that down is partly a negotiated direction. Your body is also adapted to ignore the rotation. You grew up inside this rotating frame, so your baseline includes it, and your motor system learned what to expect. The floor does not feel like it is pulling sideways because you learned its rules early, and because the forces remain almost constant from moment to moment. The same logic extends upward in layers. Earth rotates, then Earth orbits the Sun, and the solar system moves within the Milky Way, while the Milky Way moves within a larger neighborhood. Each layer is real motion with real speeds, yet each is mostly hidden because the ride is smooth. This stacked motion is the core premise of the film. We are not travelling in one simple direction at one simple speed. We are riding a layered conveyor of cosmic movements at once, like nested gears turning inside one another, each gear too large to sense from the inside. Layer 1 is rotation, Layer 2 is orbit, Layer 3 is the Sun's path through the galaxy, Layer 4 is the Milky Way's motion within its local environment, shaped by gravity and the distribution of nearby mass. The names are simple, but the consequences are profound, because each layer changes what here means. Beyond that, the local group drifts relative to nearby groups and clusters. On larger scales, matter streams along filaments toward dense regions, guided by gravity acting over hundreds of millions of light years. Beyond even that, space itself expands, stretching the distances between faraway galaxies as the universe evolves. Each layer adds speed, but the feeling of speed does not add. Your senses do not sum velocities into a single sensation, because biology does not compute motion that way. They react to forces, vibrations, and changes that break the shared smoothness, and they ignore the steady background that would otherwise overwhelm perception. This is why the question matters. If you cannot feel most of your motion, you might assume it does not exist, and that assumption feels reasonable in daily life. That assumption breaks when you start asking what you're moving relative to, because the answer depends on the frame you choose. Frames of reference are the key. Speed is not an absolute property in classical terms. It is a relationship between an object and a chosen frame, and the frame can be a train car, a planet, the distant stars, or a cosmological background. On a train, you can be at rest relative to your seat. You can be moving relative to the station, and moving at a different speed relative to a car on a nearby road. All statements can be true at once because each uses a different reference, and each reference defines its own still. Earth's rotation is obvious relative to the stars, but not relative to your room. Your room is bolted to the same spinning planet, and the air around it largely shares the rotation as well. The shared frame erases the sensation, leaving only small residual effects that careful experiments can detect. Relativity sharpens this lesson. There is no universal state of rest that everyone must agree on, and observers in uniform motion can each call themselves stationary while physics still works. The laws of nature do not require a privileged platform, and that is one reason the universe can be described consistently from many viewpoints. That sounds like it dissolves the documentary's claim. If motion depends on a reference, then saying we move through the universe seems meaningless, like a poetic phrase rather than a measurement. Yet the desire behind the phrase is understandable, because we want a map that does not depend on our local conveniences. But the universe gives us ways to choose useful frames. Some frames are more convenient because they simplify the large-scale picture, and they reduce messy motions into clearer patterns. Convenience is not absolute rest, but it can look like a cosmic standard when it aligns with the average behavior of matter and radiation. This is where tension enters. We will keep saying we move through space, yet we must define the space we mean, and we must justify the comparison we're making. We must decide what we are moving relative to, and why that choice matters for what we claim to know. One candidate frame comes from cosmology. The cosmic microwave background fills the sky with ancient light, arriving from every direction as a faint microwave glow. It is the cooled afterglow of the early universe, released when the cosmos first became transparent, and then stretched by expansion into longer wavelengths. In visuals, it is not a bright object but a uniform haze, a nearly perfect backdrop behind galaxies and stars. Its temperature is about 2.7 Kelvin, only a few degrees above absolute zero, and it is astonishingly smooth. That smoothness is the point, because tiny variations encode the seeds of later structure. If you move relative to that background, its temperature looks slightly different in different directions. One side of the sky becomes a bit warmer, the opposite side a bit cooler because motion Doppler shifts the radiation. This dipole pattern acts like a speedometer, turning a subtle asymmetry into a measurable velocity. That sounds like a preferred frame, almost like a return of absolute rest. It is not absolute in the old philosophical sense because the laws of physics still work in any inertial frame. Still, it is special in practice because it is tied to the universe's large-scale matter and radiation, and it gives cosmology a natural reference for average motion. So the film's central question becomes sharper. If motion is relative, why do some measurements point to a cosmic rest frame anyway? And why does the universe offer a background that behaves like one? If we can define such a frame, what does it reveal about our true speed, and what does it hide about the deeper nature of space? Before we climb to those larger layers, we start with what we can test nearby. Earth's rotation is not just a number, it is a motion humans proved with clever experiments, long before spacecraft and satellite tracking made the planet's spin feel obvious. For centuries, rotation was debated because it is hard to feel. If Earth spins, why do we not fly off? And why do we not feel wind screaming past at 1,000 miles per hour? These questions were not naive. They were reasonable challenges in a world where motion meant jolts, gusts, and visible displacement. The answers are physical, not rhetorical. Gravity holds us down, and the atmosphere co-rotates with the planet, dragged along by friction and constrained by the same gravitational field. The ground, the air, and your body share nearly the same angular velocity, so there is no constant blast of wind simply from rotation. What remains are subtle mismatches, and those mismatches are where science lives. The equatorial bulge shows that rotation reshapes the planet, because a spinning body tends to widen at its middle under centrifugal effects. Earth is not a perfect sphere, and that slight flattening is a fossil record of ongoing rotation. The Coriolis effect bends winds and currents because moving air crosses a rotating frame. It does not create motion from nothing, but it deflects motion that already exists, turning straight paths into arcs. In satellite imagery, that deflection becomes visible as spiraling storms and large-scale ocean gyres, patterns drawn by rotation on a fluid canvas. A swinging pendulum can reveal rotation without leaving the room. The Foucault pendulum's plane of swing appears to rotate over time, a slow, dignified drift that feels almost theatrical in a quiet hall. It is not the pendulum turning, but Earth turning beneath it, and the rate of that apparent rotation depends on latitude. Historically, that mattered because it made Earth's rotation public and local. You did not need a telescope or a voyage. You needed a long wire, a heavy bob, and patience, and the planet would reveal itself by changing the floor beneath a steady swing. Gyroscopes also keep their orientation in space because of angular momentum. When mounted on Earth, they seem to drift because the ground rotates under their conserved axis, and that drift can be measured with precision instruments. In modern navigation, gyroscopes became practical tools, but they also remain philosophical objects, proof that straight can be defined without looking outside. These demonstrations matter for the story. They show that imperceptible motion can still be real and measurable, and that the absence of sensation is not the absence of dynamics. They also show how a frame can hide motion until you compare it to something that does not share it, whether that something is a pendulum's inertia or the distant stars. The documentary will keep repeating that method. Find a reference that does not ride along, measure the mismatch, then translate it into speed, direction, and consequence. The art is choosing the right reference, because the wrong one can make a real motion look like noise. For now, the first reveal stands. At the equator, you're moving about 465 meters per second, and that motion is as real as any highway speedometer reading. You're already faster than sound, and you did not need to notice, because your body is not built to celebrate steady velocity. Yet that is only the first layer. Rotation is the smallest of the big motions we will stack, and it is the one most tightly shared by everything around you. The next layers will dwarf it in speed and scale, and the feeling of stillness will remain because smoothness is the great disguise. So we end where we began, in the chair, but with a different premise. Stillness is a perception, not a guarantee, and perception is tuned for survival rather than cosmic bookkeeping. Your brain reports stability because stability is useful, and because constant backgrounds are filtered away. The universe does not care what feels useful. It moves in layers, and it leaves clues in pendulums, in stars, and in ancient light. Clues that become clearer when we stop trusting sensation as our primary instrument. The question is which clues we trust, and what frame we choose, when every frame tells a slightly different story. Next, we step beneath the illusion and follow the first mechanism. We track Earth's rotation in numbers and in experiments, then use it as a ladder to the wider cosmos, where the background itself may offer a kind of reference. If stillness is a trick, the next step is learning how the trick is done. We start with the same quiet problem from Chapter 1, the kind that hides in plain sight. If motion is real, why does the room feel nailed down? Why does the floor feel like an anchor instead of a moving platform? Earth's first hidden engine is rotation, and it is almost insultingly steady. It is shared by nearly everything around you, and because it is shared, it becomes easy to ignore. The planet turns whether you are awake or asleep, whether the sky is clear or clouded, and the turning is so consistent that the nervous system files it under normal. A solar day is the rhythm of clocks and sunlight, the interval from one noon to the next. A sidereal day is the planet's true turn against the stars, measured relative to distant points that barely shift on human timescales. That sidereal day is about 23 hours and 56 minutes, which sounds like a technical footnote until you notice the missing 4 minutes. Those minutes are not lost. They are the price of Earth advancing along its orbit while it rotates. By the time Earth has completed one true spin, it must rotate a little extra to bring the Sun back to the same place in the sky. Quantify the spin and the mystery sharpens, because numbers refuse to be soothed by intuition. Earth's angular speed is about 1 rotation per sidereal day, roughly 729 at 10 euros 5 radians per second. That is a small number in radians, yet it multiplies into enormous linear speeds when the radius is large. At the equator, that angular speed becomes a linear speed near 465 meters per second, because the equator traces the larger circle. That is about 1,670 kilometers per hour, a highway speed multiplied by 20, carried quietly by bedrock and ocean. The speed is not uniform across the surface, and that detail matters because it reveals the geometry. It depends on latitude because circles of rotation shrink toward the poles, like smaller and smaller rings stacked on a globe. At latitude F, the eastward speed scales roughly with cos F, because the effective radius of the circle is r cos F. At the poles, it falls to essentially 0, where the axis passes through and the circle collapses to a point. This is the first lesson in stacked motion, and it is more personal than it sounds. Your speed depends on where you stand, even before leaving Earth, and the difference is large enough to matter in careful measurements. A person at the equator is moving east, faster than a person in London, even though both share the same day. So why do you not feel it, when the numbers are so dramatic? Because your body mostly detects changes in motion, not constant motion, and it is tuned to acceleration rather than velocity. A car that accelerates pins you to the seat, while a car that cruises smoothly becomes background. Earth's rotation is close to constant angular velocity, and that constancy is the trick. A nearly unchanging rate produces no persistent alarm signal, because the sensors adapt and the brain recalibrates. What would feel strange is a sudden change in spin, not the steady turning itself. You also share the frame with the floor, the walls, and most of the air. Shared motion erases local comparison, because everything you can push against is moving with you. Without an external reference, the room becomes its own universe, internally consistent and therefore deceptively calm. Gravity dominates the force budget, and it sets the baseline that your body cools down. The centripetal acceleration from rotation is small compared with g, so it only slightly modifies the weight you feel. In everyday life, that modification is too subtle to announce itself. At the equator, the centripetal acceleration is about 0.034 meters per second squared, only a few thousandths of gravity. If you could turn rotation off, you would weigh slightly more at the equator, and the difference would be measurable on a sensitive scale. Yet it would not feel like a lurch, because it is not a sudden change in your personal motion. Your inner ear can detect angular acceleration, and it is excellent at detecting starts, stops, and tilts. It does not report a constant spin when the fluid settles into baseline, because the semicircular canals respond to relative motion of fluid, not the steady state. After a brief transient, the system returns to equilibrium and the sensation fades. The brain subtracts steady backgrounds, and that subtraction is a survival feature. Stillness becomes a perception of unchanging forces, not a proof of rest, and the difference is crucial. The world can be moving quickly while the forces remain stable, and stability is what the body trusts. Early observers did not have accelerometers, or gyros in their pockets, or satellites overhead. They had the sky, and the sky seemed to rotate every day with a precision that looked like a cosmic mechanism. The simplest evidence was also the most misleading, because it encouraged the wrong culprit. Night after night, stars rise in the east and set in the west, and the pattern repeats with uncanny reliability. The entire dome appears to turn around a fixed axis, with the North Star hovering near the pivot in northern latitudes. In the south, Other stars trace circles around a different invisible point, because the axis pierces the globe in two places. For a long time, the simplest story was that the heavens moved, and Earth did not. Earth felt heavy and central, so it seemed still, and the sky felt light and mobile, so it seemed to spin. That story also fit a human-centered intuition, where the stage stays put and the scenery moves. But the daily rotation of the sky is also consistent with a rotating Earth, and that is where the evidence had to become indirect. If you cannot feel the motion, you must find a test that does not rely on sensation. You must create a situation where Earth's rotation cannot hide inside shared movement. The conceptual leap was not just mathematical, and it was not just a new diagram in a book. It was psychological, because it asked people to distrust sensation and to treat the senses as instruments with known limitations. It also asked them to accept that the obvious frame, the ground, might be the one in motion. If Earth moves, why do dropped objects land near the base of a tower, instead of falling behind as the tower races east? Why are there not constant violent winds, screaming westward as the surface outruns the air? These questions are not naive. They are the natural objections of a mind trying to keep cause and effect intact. The answer is that motion can be shared, and shared motion is hard to detect without an outside reference. A dropped stone already has the tower's eastward speed before release, because it was moving with the tower while it rested on the ledge. When you let go, you do not erase that horizontal velocity. It keeps that speed as it falls, aside from small changes due to air drag and the geometry of the fall. So it lands close to where it started, and the experiment does not refute rotation. In fact, the tiny deviations that remain, if you measure carefully enough, become part of the evidence. The air also largely co-rotates with Earth, and that co-rotation is maintained by friction and pressure coupling near the surface. Gravity holds the atmosphere close, and viscosity and turbulence transmit momentum upward, so the bulk of the air shares the planet's spin. Winds exist, but they are departures from a rotating baseline, not a separate stationary ocean of air. So the key is to find a reference that does not fully share the spin, or a behavior that resists being dragged along. Inertia becomes the witness, because inertia is the tendency of motion to keep its state unless acted on. If Earth is rotating, inertia should reveal a mismatch between what the ground calls straight and what space calls straight. Inertial frames are the frames where free motion stays straight and uniform, and where Newton's first law holds without extra terms. Rotating frames are not inertial, even if they feel calm, because the axes themselves are turning. The discomfort is conceptual. A frame can feel stable while still being dynamically non-inertial. On a rotating Earth, straight motion in an inertial sense can look curved when you describe it from the surface. That apparent curvature is a clue, and it is the kind of clue science loves because it is systematic. It does not depend on mood, belief, or the quality of your senses. This is where physics starts to look different, and where language becomes careful. The same path can be described as straight or bent depending on frame, and neither description is wrong if you keep track of the reference. What changes is the bookkeeping, and the bookkeeping determines what forces you must include. In a rotating frame, extra terms appear in the equations of motion, and they are not optional. They are called fictitious forces, but their effects are real, measurable, and repeatable. The name fictitious refers to their origin in coordinates, not to their consequences in the world. Centrifugal effects push outward from the rotation axis, and they slightly reduce effective gravity. Coriolis effects deflect moving objects sideways relative to the surface, and the deflection depends on speed and latitude. Together they form the signature of rotation, written into trajectories that would otherwise be simple. These are not new forces acting from nowhere, like invisible hands in the air. They are bookkeeping terms that arise when the reference frame turns, and they keep Newton's laws usable on a rotating planet. In a sense, they are the price you pay for insisting that the ground is your coordinate system. The documentary's central question tightens here, because the mystery becomes technical. If stillness is local agreement, which frame is doing the agreeing, your senses, the ground, or the wider space in which the ground is turning? And if multiple frames can be right, what does it mean to claim that something truly moves? The first dramatic proof that Earth rotates can happen indoors, away from the sky and its ancient arguments. You do not need to look at the stars, and you do not need to trust a telescope. You only need a heavy bob, a long cable, and patience. A Foucault pendulum swings in a plane set by its initial push, and that plane is the star of the experiment. In an inertial frame, the plane stays fixed because the pendulum's motion is governed by inertia and gravity. The swing traces a repeating path, and the direction of that path has no reason to rotate by itself. But the floor beneath the pendulum is attached to Earth, and Earth is turning. As Earth rotates, the swing plane seems to slowly turn relative to the building, like a silent hand sweeping across a compass rose. The effect is slow enough to watch and steady enough to trust. The pendulum is not twisting itself, and it is not secretly powered by the building. The building is rotating under a motion that tries to remain in one plane, and the mismatch becomes visible as precession. The air seems to hold a fixed direction while the architecture slides beneath it. In a museum hall, the visuals are almost theatrical. The bob glides back and forth, cutting a line through the air while a ring of pegs waits on the floor like a clock face. One by one, the pegs fall, and the audience watches Earth confess without a word. The rate of this apparent precession depends on latitude, and that dependence is the key. It is fastest at the poles and vanishes at the equator, which is exactly what a rotating sphere predicts. At the pole, the ground rotates under the pendulum once per sidereal day, so the plane appears to complete a full turn. At latitude F, the precession rate is proportional to sin F, a simple function with deep meaning. The full rotation rate appears only at the pole, while intermediate latitudes show partial precession. The formula is not just a calculation, it is a fingerprint that matches a globe rotating about a fixed axis. This latitude dependence is the signature because it connects geometry to observation. It tells you that the effect is not a trick of the apparatus and not a local draft in the hall. It is global, tied to Earth's axis, and it changes predictably as you move north or south. Foucault's point was not only proof, and that is why the pendulum became famous. It was a method that makes Earth's rotation measurable without astronomy, without waiting for seasons, and without interpreting ancient star catalogues. It brought a cosmic claim down to the scale of a room. There is also a historical resonance here, because the pendulum arrived after centuries of debate about motion. By the 19th century, the mathematics of rotating frames was mature, but public intuition still lagged behind. Foucault's demonstration was persuasive precisely because it was visible, slow, and stubbornly repeatable. It also teaches a deeper idea, one that will echo later in the story. A rotating frame changes what counts as a fixed direction, even when everything feels still. North and east remain useful, but they do not point to a rigid grid in space, and the pendulum makes that discomfort tangible. In an inertial frame, the pendulum's plane is stable, and stability means constancy in space. In the Earth frame, stability becomes a slow drift, and drift is what you see on the floor. The same motion carries two descriptions, and the difference between them is the rotation of the observer. That drift is evidence written in the air, and it is strangely intimate. It is the mismatch between inertia and the turning ground, made visible by a mass on a string. The pendulum does not argue, it simply keeps swinging, and the world rotates beneath it. Gyroscopes tell the same story with a different instrument, and the visual language changes from graceful arcs to stubborn orientation. A spinning rotor resists changes to its axis, and that resistance is not mystical. It is angular momentum, conserved when external torques are small. Because of angular momentum, a well-isolated gyroscope keeps its orientation in inertial space for long periods, like a pointer aimed at an invisible star. On Earth, that looks like the gyroscope is drifting, because the platform beneath it is turning. The apparent motion is again a disagreement between frames. In laboratories and aircraft, this becomes practical rather than philosophical. Modern inertial navigation systems exploit this, treating gyroscopes as local references that do not fully share Earth's turn. When GPS is unavailable, these systems can still estimate attitude and motion by integrating measured rotations and accelerations. The measurement is not a metaphor, and it is not a matter of belief. It is engineering, and it works because rotation is a physical parameter with measurable consequences. If the planet were not rotating, the error budgets and correction terms would look different, and the instruments would not behave as they do. Now widen the scale without leaving the room. The same rotation that hides from your senses shapes the entire planet, and it does so continuously over geological time. The evidence is not only in moving objects, but in Earth's very figure. Earth is not a perfect sphere, and the reason is not merely mountains and trenches. Rotation produces an equatorial bulge because outward centrifugal effects reduce effective gravity more at the equator than at the poles. Over long times, rock flows like a very stiff fluid, and the planet relaxes toward an equilibrium shape. The equatorial radius is larger than the polar radius, and the difference is large enough to measure with ordinary numbers. Earth is an oblate spheroid, slightly flattened at the poles, with an equatorial radius about 21 kilometers greater than the polar radius. That flattening is a quiet record of persistent spin. This bulge is not a one-time accident, and it is not a cosmetic detail. It is maintained by ongoing spin and the planet's ability to deform over geologic time through mantle convection and viscoelastic relaxation. If Earth stopped rotating, the bulge would slowly subside and the oceans would migrate. Geodesy measures Earth's shape with extreme precision, treating the planet as a figure defined by gravity and rotation. In geodetic language, the geoid is an equipotential surface, an idealized sea level shaped by mass distribution and centrifugal effects. It is lumpy, subtle, and deeply informative. Long before satellites, surveyors saw hints in arc measurements and gravity variations, and the hints were unsettling. The numbers did not fit a perfect sphere, and they did not fit every assumption about uniform density. Expeditions measured meridian arcs in different latitudes, and the results supported a flattened Earth. With satellites, the confirmation became unavoidable, because orbits are sensitive to Earth's mass distribution. A satellite feels the planet's gravity field, and that field reflects oblateness, as well as smaller anomalies from crust and mantle structure. The orbit precesses in ways that can be predicted only if the bulge is real. Satellite tracking maps the geopotential, turning minor changes in orbital elements into a portrait of Earth's interior and surface. It reveals the equatorial bulge and smaller anomalies from mountains, trenches, and mantle density variations. What looks like a smooth blue marble from afar becomes in gravity a textured landscape. Rotation also leaves a fingerprint in weight, and you can describe it without exotic instruments. Effective gravity is slightly weaker at the equator than at higher latitudes, and the difference comes from two sources. Part of it is centrifugal reduction, and part is Earth's larger equatorial radius, which places you farther from the center. These differences are small but measurable, and they matter in precision work. They show that rotation is not an abstract claim, but a term in everyday forces, quietly included in the number your scale reports. Even down is slightly different depending on where you stand. The atmosphere is where rotation writes its most dynamic evidence, because air is free to move and quick to respond. Air moves because of heating, pressure gradients, and terrain, and those drivers create flows across continents and oceans. Once air is moving, Earth's rotation deflects it, and the deflection organizes weather. That deflection is the Coriolis effect, and it is often described as if it were a mysterious sideways push. Coriolis is not a push that starts motion, and it cannot create wind from still air. It is a sideways acceleration that appears when you describe motion in a rotating frame, and it depends on the object's velocity. Mathematically, the Coriolis acceleration is proportional to 2 v, which means it depends on Earth's rotation rate and the speed of the moving air. The direction comes from the cross product, which is a formal way of saying the deflection is perpendicular to the motion. The plain language version is simple. Moving things get nudged sideways on a spinning planet. In the northern hemisphere, motion is deflected to the right of its path, and that rule is reliable for large-scale flows. In the southern hemisphere, it deflects to the left, mirroring the geometry of the rotating frame. The effect is zero at the equator and strongest near the poles, because the relevant component of Earth's rotation changes with latitude. Again, latitude dependence becomes the diagnostic, the repeating theme of this chapter. The planet is not merely spinning, it is spinning around a particular axis, and the consequences know where that axis is. When the sign flips across the equator, it is as if the world announces its geometry. A rotating carousel makes the idea accessible, because you can see the disagreement between frames. Walk straight across and you appear to curve to someone riding the platform, even if you aim for a fixed point. From above in an inertial view you went straight, but from the rotating view your path bends because the frame turned under you. Earth is that carousel but enormous, and the scale changes everything about what you notice. The sideways deflection is small for short distances and large for long ones, because the acceleration acts over time. A thrown ball across a room will not curve noticeably, but a moving air mass over 1,000 kilometers will. Trade winds are shaped by this, and they are among the most persistent patterns on the planet. Air moving toward the equator is deflected westward, helping set up steady wind belts that sailors learned to trust long before they could explain them. The winds are not random. They are constrained by rotation and heating. Mid-latitude westerlies are shaped by it too, and they dominate much of the weather in temperate zones. The global circulation becomes organized into bands rather than simple north-south flow, because Coriolis resists direct meridional motion. The result is a planet with preferred corridors of wind, like invisible rivers in the sky. Cyclones reveal the effect in a form people recognize because the spiral is dramatic. Large storms rotate because inflowing air is deflected as it converges toward low pressure, and the deflection builds a coherent spin. The direction of spin differs by hemisphere, and the pattern is not magic, it is rotation acting on moving air. In satellite imagery, the visuals are unmistakable. Cloud tops curl into comma shapes, spiral bands wrap around calm eyes, and the whole system seems to breathe as it rotates. The storm is not merely moving across the map, it is a rotating structure, stabilized by the same physics that governs a pendulum's drift. The common myth about draining sinks is not the point, and it distracts from the real scale of the phenomenon. The Coriolis effect is too weak at that scale to dominate, because the time and length scales are too small and local disturbances overwhelm it. At the scale of weather systems, it becomes decisive, because small deflections accumulate over days. Ocean currents also carry the signature, and they do so with enormous climatic consequences. Moving water is deflected, shaping gyres and influencing heat transport from equator to pole. The ocean becomes a slow conveyor of energy, and rotation helps determine its pathways. Coriolis matters for projectiles as well, and here the evidence becomes operational and measurable. Long-range artillery and ballistic trajectories must correct for Earth's rotation, because the ground moves under the flight path. The shell is not simply flying over a static map. The map itself is turning. A shell fired north or south does not land exactly where a non-rotating model predicts, because the launch point and target have different eastward speeds. The correction depends on latitude, direction, and time of flight, and it can be calculated with the same rotating frame terms used for winds. In practice, the corrections are built into firing tables and guidance systems. These are the same physics in different costumes, which is part of the chapter's quiet elegance. Pendulums, storms, and shells all reveal a rotating frame, and they do so without needing a cosmic reference in the moment. Each case is a comparison between inertia and a turning surface, so the chapter's structure becomes a chain of indirect proofs, and the chain is stronger than any single link. Each proof compares earthbound motion to inertial behavior, and each finds a systematic mismatch. The mismatch is not noise, it is the signal. First, the sky's daily turn suggests a rotation somewhere, and it invites the question of which body is responsible. Second, inertia-based devices show the ground turning beneath them, and they do it indoors where the sky cannot be blamed. Third, moving fluids and projectiles curve in systematic ways that match the mathematics of a rotating sphere. Fourth, Earth's shape and gravity field record long-term spin, as if the planet has been moulded by its own motion. None of these require you to feel rotation directly, and that is the point. They require you to measure what changes when frames disagree, and to treat that disagreement as evidence. This is why the story is a mystery, even though the answer is familiar. The culprit is constant motion, and the evidence is always in the residuals, in the small differences that remain after you subtract what is shared. Science often lives in those leftovers, where intuition stops being reliable. Once you accept rotation, you can quantify your own speed precisely, and the number depends on latitude and Earth's radius. At the equator, the surface speed is about 465 meters per second, and the horizon is sweeping east faster than sound travels in air. Yet the sweep is so smooth that it feels like nothing. At 45 degrees latitude, it's about 329 meters per second, and the difference is not trivial. Near 60 degrees, it drops to about 233 meters per second, and by the time you approach the polar circles, the linear speed has fallen dramatically. The planet gives different riders different velocities, even though the day feels the same. Yet everyone shares the same angular speed, 1 turn per sidereal day, and that shared rate is the global fact. The rotation is global even when speeds vary locally, and that distinction matters later. Angular measures connect to the whole Earth, while linear measures depend on where you are. The same distinction will return with the orbits, and it will be emotionally harder to accept there. A shared angular motion can hide enormous linear speeds, and the numbers can become so large that the mind tries to reject them. Rotation is training for that discomfort, because it already hides a kilometre per second world inside a quiet room. Now introduce the frame language explicitly, because the chapter has been using it in practice. An inertial frame is an ideal where Newton's first law holds cleanly, and where free objects move in straight lines at constant speed, unless forces act. Earth's surface is not an inertial frame because it rotates, even if it feels like a natural place to stand. To use Earth's surface as a frame, we add centrifugal and Coriolis terms, and we do it systematically. Those terms are sometimes called fictitious, but the name is misleading if you confuse origin with effect. The forces are not fundamental interactions like gravity, yet they are consequences of describing motion from a turning platform. This is the deeper answer to why the universe feels motionless, and it is both comforting and unsettling. Your daily frame is rotating, but it is stable and shared, so it becomes the default definition of at rest. Your senses evolve to detect immediate threats, and they do not naturally separate inertial truth from rotating convenience. Science does that separation by building references, and by insisting on reproducible comparisons. It uses pendulums, gyroscopes, telescopes, and satellites as witnesses, each with its own strengths and vulnerabilities. Each witness is imperfect, and each must be calibrated, corrected, and interpreted within a model of frames. That is also the warning embedded in the central question, and it is worth lingering on. Measurements reveal motion, but only relative to chosen standards, and standards are human choices guided by physics. When the standards change, the description changes, even though the underlying events do not. Even the sidereal day is defined by a reference, and it is a carefully chosen one. It is Earth's rotation relative to distant stars, treated as fixed, because their apparent motion is slow on the timescales of clocks. That choice makes the day a clean measure of spin, separated from Earth's orbital progress. Those stars are not truly fixed, and the chapter does not need to pretend they are. Over long times they move, and Earth's axis itself slowly precesses, like a top tracing a circle over millennia. For this chapter, the approximation is enough, because the stars provide a stable backdrop on human timescales. The point is not that we found absolute rest, and it never was. The point is that we found reliable comparisons that expose hidden motion, and that reliability is what science demands. The world may not offer a universal still point, but it offers patterns that can be tested and trusted. Rotation also connects to timekeeping, and the connection is more than historical. The difference between solar and sidereal days shows how orbital motion complicates simple cycles, and it reveals that even one day is not a single concept. It hints at the next layer, because Earth's rotation is measured against the stars, but the Sun's position is tied to orbit. So even our daily experience of time already mixes two motions, and the mixing is invisible unless you look for it. The clock face hides a moving geometry, and the geometry is the true machinery behind the familiar rhythm. When you say tomorrow, you are already speaking the language of combined motions. This is the chapter's closing turn, and it is meant to feel like a door opening. We have proven a motion that feels absent, and we have learned how to prove it without relying on sensation. We used the sky as the first clue, inertia as the courtroom witness, and fluids and shape as corroboration. The conclusion is not just that Earth spins, but that smooth motion can be measured with precision anyway. That precision is unsettling, because it means the universe can move you quickly, while giving you no sensation of speed. It also means we can climb the stack, because if we can detect rotation from inside the rotating world, we can detect larger motions too. Rotation is only the first layer. Now the entire rotating Earth is also racing around the Sun. Next we follow that second engine. We test orbital motion with new clues, and the speeds become harder to emotionally accept. Rotation was only the first layer. The entire spinning Earth is also in orbit, falling around the Sun at enormous speed. In wide shots the planet looks serene, cloud bands curling like brushstrokes, yet the whole sphere is sliding sideways through space without pause. The Sun is not pulling us along a rail, it is drawing us inward, and Earth answers by moving forward, turning a fall into a loop. If the camera pulls back far enough, the stillness becomes almost suspicious. The continents do not blur, and the oceans do not slosh outward, because orbital motion is not like a car taking a sharp turn. It is a continuous curve, and the curve is the point. Earth's average orbital speed is about 29.78 kilometers per second. That is about 107,000 kilometers per hour, every day. The number sounds abstract until you anchor it to human scales, because the brain evolved for thrown stones and running feet. A rifle bullet might travel near 1 kilometer per second, sometimes less, sometimes more. Earth is moving around the sun roughly 30 times faster than that bullet. The comparison is imperfect, but it forces intuition to wake up. A commercial jet cruises near 250 meters per second, around 900 kilometers per hour, and even that speed feels dramatic when you watch clouds shear past a window. Earth's orbital motion is more than 100 times faster. If you could freeze the sky and lay a ruler along Earth's path, the planet would cross the width of a major city in a heartbeat. In a single second, it moves almost 30 kilometers, which is farther than most people commute in a day. Speed at this scale is not something we sense directly. It is something we infer because the evidence lives in geometry and timing. Even a fast rocket during ascent is not automatically faster than Earth's orbit. Many rockets spend their first minutes fighting gravity and air, not building orbital velocity. In launch footage, you can see the trade being made, flame and shock diamonds below, thick atmosphere thinning above, because the rocket must buy sideways speed while paying the tax of climbing. Only later, when the air is gone, does the vehicle start to behave like an orbital machine. That sideways speed is not a metaphor. In low Earth orbit, spacecraft travel around 7.8 kilometers per second relative to the ground, and that is still only a fraction of Earth's speed around the Sun. Orbital motion stacks, layer on layer, and each layer is easy to miss from inside it. This is the first terrifying twist of the chapter. The speed that keeps us alive is also the speed that could fling us into deep space. It feels like a contradiction, because we associate safety with stillness and danger with motion. In orbital mechanics, safety is not the absence of speed. Safety is the right speed, in the right direction, at the right distance. Orbit is not a track carved into space. Orbit is a motion you keep only by continuously missing the thing you are falling toward. The simplest picture is Newton's cannon thought experiment. Fire a cannonball fast enough and it falls, but the ground curves away. At low speed, it hits the ground. At higher speed, it travels farther before impact, because Earth's surface drops beneath it. At a critical speed, the fall never ends. The projectile keeps falling, but the planet keeps curving away at the same rate. In animation, the arc becomes a circle, then an ellipse, while the cannon stays fixed on a mountain, quietly implying that orbit is not mystical. It is geometry plus gravity, repeated every moment. That image also hides a detail Newton understood with unusual clarity. The cannonball is not choosing to go around, it is trying to go straight, and gravity keeps bending that straight line into a closed path. That is orbit in one sentence. It is perpetual free fall, stabilized by sideways motion, and the shape of space around a massive body. Gravity provides the inward acceleration. Inertia provides the tendency to keep moving straight, which becomes a curved path under gravity. In Newton's language, the inward pull supplies centripetal acceleration, which is simply the acceleration needed to keep turning. The path curves not because the object wants to curve, but because it cannot stop being pulled. For a near-circular orbit, the needed inward acceleration is v squared over r, a compact rule that links speed to curvature. Increase the speed while keeping the same distance, and the required inward pull rises sharply. That is why orbital velocity is not just fast, it is fast in a mathematically constrained way. The balance is precise but not fragile in the everyday sense. Small changes in speed shift the orbit, but do not instantly destroy it. A slight increase in speed raises the far side of the orbit, its aphelion, while a slight decrease lowers it, tightening the loop toward the Sun. The orbit responds smoothly, like a system that remembers its rules. Still, the balance is precarious in principle. Too slow and you spiral inward, too fast and you escape. Escape is not a cliff you step over by accident, yet it is a real threshold. Above it, gravity still pulls, but it cannot pull enough to turn your path into a closed curve. Escape velocity near Earth's surface is about 11.2 kilometers per second. Earth's orbital speed around the Sun is much higher, because the Sun's gravity well is deeper. At Earth's distance from the Sun's escape velocity is about 42 kilometers per second. Earth's 29.78 kilometers per second sits below that edge. That difference matters for the story. We are fast enough to circle the Sun, but not fast enough to leave it without extra energy. In other words, our sideways speed is large, but it is not unlimited. We live inside the Sun's gravitational domain, its long, invisible basin, where the cost of departure is measured in kilometers per second. You can feel the logic without doing the math. If you want to climb out of a valley, you need more than momentum. You need enough energy to keep climbing even as the slope keeps resisting. So why does the universe feel motionless? Because orbit is mostly constant velocity, and constant velocity is quiet to the body. Your inner ear is tuned to acceleration. Orbit involves acceleration toward the Sun, but you do not feel it as a shove. The acceleration exists, and it is not trivial, yet it is steady and shared. It is the same kind of subtlety that makes a smooth elevator ride feel like nothing, until it starts or stops. You do not feel it because you and everything around you share it. The whole Earth is accelerating together, so there is no local mismatch. This is the same logic as rotation, but scaled up. Shared motion hides evidence, unless you compare to something not sharing the ride. That something is often light, because light carries information from far away without caring about our local habits. It arrives with a direction, a colour, and a timing that motion can distort. Now the chapter turns to a deeper confusion. If orbit is free fall, why do you feel weight on Earth's surface? Weight is not gravity itself. Weight is the normal force, the push of the ground preventing you from falling. Gravity pulls you downward with forcing. The ground pushes upward with an equal normal force, and that push is what your body senses. The distinction sounds technical, but it is physically intimate. Your bones compress, your skin deforms, and your organs settle because the floor is pushing back. That push is what heavy feels like. If you stand on a scale, the number it shows is not how much gravity you have. It is how hard the scale must push upward to keep you from accelerating downward. The reading changes in an elevator, not because gravity changes much, but because support changes. In free fall, gravity still acts. The difference is that there is no supporting surface, so the normal force drops towards zero. That is why astronauts feel weightless in orbit. They are not beyond gravity, they are falling with their spacecraft. The spacecraft is also falling, so it does not press on them. Their bodies float because nothing is holding them up against gravity. In slow-motion footage, a loose tool drifts beside a gloved hand, and a droplet of water becomes a trembling sphere, surface tension replacing down. Gravity is present, but support is absent. The visual is beautiful, but the physics is blunt. In low Earth orbit, gravity is still strong, only modestly weaker than at the surface. Weightlessness happens because everything nearby shares the same fall, so nothing needs to push on anything else. On Earth's surface, you are not in free fall. The ground constantly accelerates you upward relative to your natural falling path. That upward acceleration is small in distance but continuous in time. It is the everyday miracle that makes a floor feel solid. A useful way to picture it is to imagine your freefall path as a curve Earth would like you to follow. The ground interrupts that curve every instant, forcing you to deviate from it. This distinction is essential for the central question. Motion can be huge and still feel like nothing when forces remain steady. It also hints at why speed is not the whole story. What matters to sensation is change. Change in speed, change in direction, change in support, and orbit hides those changes by distributing them smoothly. Earth's orbit is also the machinery behind the seasons, but not in the way people first guess. The seasons are not caused by changing distance alone. Earth's orbit is slightly elliptical, and the distance to the Sun changes through the year. The effect on sunlight is real but modest. At perihelion, Earth is about 147 million kilometers from the Sun, and at aphelion it is about 152 million kilometers away. That difference sounds large, yet it changes solar energy by only a few %. That small change is measurable, and satellites can see it as a slight breathing of the solar constant. Yet it cannot explain why snow piles up in Boston while beaches fill in Sydney at the same moment. The geometry of sunlight matters more than the raw distance. The dominant cause of seasons is axial tilt. The tilt changes the angle and duration of sunlight in each hemisphere as Earth orbits. When the northern hemisphere tilts toward the sun, sunlight arrives more directly, and days stretch longer, two effects that compound. When it tilts away, the same land receives a shallower beam and shorter exposure. Direct sunlight concentrates energy into a smaller area, like a flashlight held close to a wall. Oblique sunlight spreads the same energy thinly, and the ground warms less efficiently. Add the length of day, and the seasonal contrast becomes inevitable. Orbit provides the calendar, and tilt provides the contrast. Together they turn steady motion into the rhythm of climate. In visual terms, the orbit is a smooth ring, while the tilt is a stubborn arrow that keeps its orientation as Earth travels. That stubbornness makes the sun climb and fall in the sky across the year. Kepler was the first to describe this orbital motion with laws that fit the data. He did it without knowing the force behind it. He worked with Tycho Brahe's painstaking observations, which were among the most precise measurements made before the telescope matured. The data were unforgiving, and they refused to fit perfect circles. Tycho's instruments were massive and mechanical, built for naked-eye precision at the edge of what craftsmanship could deliver. Kepler inherited tables of positions that were accurate to arc minutes, and he treated their discrepancies as clues rather than errors. That decision, trusting the data over the ideal, changed astronomy. Kepler's first law says planets move in ellipses with the sun at one focus. That displaced sun is the clue that motion is not perfectly circular. An ellipse is not just a stretched circle. It has a built-in asymmetry, and that asymmetry carries information about energy and angular momentum in a gravitational field. Kepler's second law says a line from planet to sun sweeps equal areas in equal times. That implies planets move faster when closer to the sun. This is not a poetic statement. It is a quantitative rule that lets you predict speed changes. Subtle for Earth, dramatic for comets, using only geometry and time. Kepler's third law links orbital period to distance. The square of the period scales with the cube of the semi-major axis. It is one of those relations that looks arbitrary until you see its power. With it, the solar system becomes a single family of motions, each orbit speaking the same mathematical dialect. These laws were not philosophical. They were predictive, and they matched the best observations of the time. Yet Kepler's laws were still descriptive. They did not explain why the laws held, or what mechanism enforced them. Newton supplied the missing engine. Universal gravitation and the laws of motion turned Kepler's patterns into consequences. Newton's gravity falls off with the square of distance. The same rule that drops an apple also curves the moon's path. That inverse square form matters because it encodes how influence spreads through space. Double the distance, and the same mass must cover 4 times the area, so the pull weakens accordingly. This was the unification that changed the meaning of motion. Heaven and Earth became one system, governed by the same mathematics. In Newton's framework, orbit is not a special state. It is what happens when gravity provides the centripetal acceleration for a given speed. You can write the balance in a single line. Gravity equals the needed inward acceleration, and suddenly the orbit becomes a solvable problem. The curve is no longer guessed, it is derived. The predictions were testable. Newtonian gravity explained why Kepler's area law reflects conservation of angular momentum. Angular momentum is the bookkeeping of rotation and orbit, and it is stubborn. When no external torque acts, the product of distance and sideways speed must adjust to stay constant. It also explained why periods scale with distance. The farther you are, the weaker gravity is, and the slower the required orbital speed becomes. The story gains tension here because stability is not the same as safety. The same equations allow long-term order and sudden disruption. A small nudge from another planet can reshape an orbit over time. Resonances can amplify small effects into large changes. In resonance, timing becomes destiny. Repeated tugs arrive in step, like pushing a swing at just the right moment. The push can be tiny, yet the outcome can be large. Comets can be kicked inward. Asteroids can be perturbed. Orbits can be stable for eons, then altered by a close encounter. Earth's orbit is stable on human timescales, but it is not guaranteed by any cosmic promise. It is maintained by a dynamic gravitational environment. That environment is mostly gentle, yet it is never silent. Every planet contributes a faint signature, and over long spans those signatures can accumulate into measurable shifts. Now we ask how we know Earth is moving. Without relying on the sun's daily path, we need evidence that points outward toward the stars. The first key measurement is aberration of starlight. In the 1720s, James Bradley found a tiny annual shift in star positions. He was searching for parallax, the long-anticipated proof that Earth orbits the Sun, yet he found a different wobble. The pattern was consistent, repeatable, and stubbornly out of phase with expectations. The shift was not parallax at first glance. It had the wrong pattern and the wrong timing for a simple change in viewpoint. Bradley's explanation was motion plus finite light speed. If Earth moves through space, incoming starlight appears tilted. Use the umbrella in rain analogy. When rain falls straight down, you hold the umbrella overhead. When you run forward, the rain seems to come from ahead. You tilt the umbrella forward, even though the rain itself did not change. Earth is the runner, and starlight is the rain. Because light has finite speed, Earth's sideways motion changes the apparent direction. In diagrams, the effect is a simple vector addition, light's velocity combined with Earth's velocity. Yet the consequence is profound. The sky itself becomes a detector for our movement. The aberration angle is about 20.5 arcseconds. That tiny number is still large enough to measure with careful instruments. An arcsecond is a sliver of angle, the kind you would associate with hairline precision. Bradley's triumph was to show that such slivers can still carry dynamical truth. It directly implies Earth's orbital speed when combined with the speed of light. It is a speedometer built into the geometry of observation. Because the aberration angle is roughly v over c, it links a human-scale speed, tens of kilometers per second, to a cosmic constant. That link is one reason the measurement feels almost magical. Aberration matters because it does not depend on the star's distance. It depends on Earth's motion and light's finite travel time. It also matters because it is hard to explain without Earth's motion. It is a clean signature of a moving observer. The second key measurement is stellar parallax. Parallax is the apparent shift of a nearby star against distant background stars. As Earth orbits, the viewpoint changes by 2 astronomical units across 6 months. The nearby star appears to wobble annually. The geometry is simple. The challenge is scale, because even the nearest stars are unimaginably far. A parsec is defined so that a star at 1 parsec has a parallax of 1 arcsecond. 1 arcsecond is 1/3600th of a degree. That definition is more than a unit choice. It is a statement about how distance is built from angle and baseline. The baseline is Earth's orbit, and the angle is the star's tiny shift. The nearest star system, Alpha Centauri, has a parallax under 1 arcsecond. Most stars have far smaller parallax angles. That is why parallax took centuries to measure. Instruments had to become precise enough to detect shifts smaller than the width of a coin, seen kilometers away. It also required patience, because the signal is annual and the sky is noisy. Temperature changes bend telescope structures, and Earth's own atmosphere smears starlight into trembling points. When parallax was finally measured in the 19th century, it did 2 things at once. It confirmed Earth's orbit and it expanded the universe. It confirmed orbit because the annual wobble matched the predicted geometry. It expanded the universe because the distances were staggering. For the first time, star stopped meaning a light on a sphere and became a sun with a location. The void between stars became an object of thought, not just an absence. Parallax turned stars from points on a dome into objects in deep space. The sky became 3-dimensional, and Earth became a moving platform. Parallax also anchored the distance ladder. Once you know distances to nearby stars, you can calibrate brighter indicators for farther ones. So the evidence arc tightens. Kepler gave patterns, Newton gave causes, Bradley gave motion through light, and parallax gave scale. In each step, the same strategy repeats. Find a subtle mismatch, measure it carefully, and let mathematics translate it into motion. The universe does not shout our speed, it whispers it into data. Now the chapter moves to the modern era, where orbit is measured with precision that feels almost unreal. Spectroscopy turns starlight into a ruler. When a source moves toward or away from you, its spectral lines shift. This is the Doppler effect for light. A spectrum is a barcode of physics, specific wavelengths absorbed or emitted by atoms, and those wavelengths are stable enough to serve as reference marks. Motion slides the whole pattern, and the shift can be measured. Earth's orbital motion adds a seasonal Doppler shift to observed spectra. Over a year, the radial component changes sign and magnitude. When Earth is moving toward a star, the lines are slightly blue shifted. 6 months later, when Earth moves away, the same lines are slightly redshifted. Astronomers correct for this with barycentric corrections. They translate observations into a frame centered on the solar system's center of mass. The correction is not cosmetic. It is required to detect small signals like exoplanets tugging on their stars. A planet can induce a stellar wobble of a few meters per second, sometimes less, and that wobble is embedded inside Earth's far larger orbital signature. Precision astronomy is the art of subtracting what you already know. Modern spectrographs can measure radial velocities at the meter per second level, sometimes better. That is precision against a background of 30 kilometers per second orbital motion. The contrast is almost absurd, like trying to hear a whispered syllable during a hurricane, yet the instruments succeed because physics is consistent, and the patterns repeat. This is another answer to the central question. The universe feels still because senses are blunt, but instruments are not. Our best measurements reveal Earth's motion as a predictable, removable pattern. We subtract it to see deeper motions beyond it. Yet the same measurements also reveal a limit. We can measure motion relative to chosen frames, but not relative to an absolute rest. Even the solar system barycenter is not fixed. It shifts as planets orbit, and the Sun itself wobbles in response. So the frame we call stable is already moving. Stillness remains a local agreement, chosen because it makes the math manageable. Now return to the speed itself, because the chapter's title demands it. Earth's orbit is like a bullet around a star, but the bullet never stops. In 1 second, Earth moves almost 30 kilometers along its path. In 1 minute, it moves nearly 1,800 kilometers. In 1 hour, it travels over 100,000 kilometers. In 1 day, it covers about 2.6 million kilometers of orbital arc. These are not exact because the orbit is elliptical and speed varies. The point is the scale, and the scale is relentless. If you could paint a line in space behind Earth, it would wrap around the Sun like a luminous ribbon, smooth, continuous, and far longer than any earthly journey. The planet is always departing, yet it always returns. The speed varies through the year because of Kepler's second law. Earth moves slightly faster at perihelion and slightly slower at aphelion. The difference is small, but it is real, and it is measurable. It is the solar system reminding us that average is a convenience, not a constant. Perihelion occurs in early January. Aphelion occurs in early July, which confuses many people who tie seasons to distance. That confusion is useful for the narrative. It shows how intuition reaches for the wrong lever, because distance feels like the obvious cause. In the northern hemisphere, January is winter, even though Earth is closest to the Sun. In the southern hemisphere, January is summer, because the tilt decides which half of the world receives the direct beam. Tilt is the real lever. Orbit is the clockwork that carries the tilted Earth through changing sunlight geometry. So the seasons are a visible consequence of orbital motion, even if they do not announce the speed directly. The calendar is a speed trace written in temperature and light. Think of the solstices and equinoxes as markers on the orbit, points where the geometry of sunlight crosses a threshold. The planet's speed is hidden, but the timing of those thresholds is not. If Earth moved faster, the year would shorten, and the seasonal rhythm would compress. If it moved slower, the same geometry would unfold more gradually, and the calendar would stretch. The seasons are not just weather. They are orbital mechanics translated into biology, agriculture, and memory. Now we underline the precarious elegance again. Orbit is stable because physics is consistent, but it is precarious because it depends on conditions. Change the Sun's mass and the orbit changes. Change Earth's speed and the orbit changes. Change the gravitational environment and the orbit can drift. The relationship is mathematical and unforgiving. Mass sets the depth of the gravitational well, and speed sets how high you climb within it. The orbit is the compromise those numbers enforce. In the long run, gravitational tugs from other planets slightly alter Earth's eccentricity and tilt. These Milankovitch cycles modulate climate over tens of thousands of years. The changes are subtle compared with daily weather, yet they leave fingerprints in ice cores and sediments. The orbit becomes a slow metronome, and climate responds in long, delayed rhythms. So the orbit is not a perfect circle repeated forever. It is a living trajectory in a crowded system. This is where the mysterious tone deepens. The calm of a year hides a complex gravitational negotiation, maintained by the math of motion. We are passengers on a curve we cannot feel. We are held by gravity we cannot touch, and guided by inertia we rarely notice. If you step outside at night, the stars look fixed and the ground feels absolute. Yet the reality is that down is a local instruction and still is a convenient illusion. What would it take to make the motion obvious to your body? Not speed, but change, an abrupt shift in direction, or a sudden loss of support, or a mismatch between you and your surroundings. The universe, at least here, is kind enough to keep the changes smooth. Now widen the scale again without leaving the room. The Sun is not a fixed center in a static universe. The Sun moves through the Milky Way, carrying Earth's orbit along like a smaller wheel mounted on a larger one. Our bullet around a star is nested inside a larger journey. In visual terms, the solar system is a moving bubble of orbits, and the bubble itself drifts through a galaxy of other moving bubbles. The nesting does not end where our senses stop. That nesting is the next step in the stack. We have measured rotation and orbit, and both were invisible until we chose the right references. Next, we follow the Sun's motion itself, and the question becomes sharper. If every frame is moving, what does it mean to say we are moving through space? We will keep the same method. Find a reference that does not share the ride, measure the mismatch, and translate it into speed. The terrifying reality is not only that Earth is fast, it is that the universe offers no final flaw, only layers of motion we can measure and subtract. And yet, for a moment, orbit looks like stability. A year repeats, seasons return, and the sky keeps time while the planet races on. That is the chapter's closing note. A bullet around a star can feel like home until you remember the speed is real and the stillness is negotiated. Rotation was the first layer, and orbit was the second, but neither was the true center. The Sun is not a fixed hub with planets circling in place, because the Sun itself is a moving object inside a moving galaxy. We ride it, and we rarely feel the ride. From Earth, the solar system feels like a self-contained clockwork, with clean cycles that return on schedule. The planets repeat their patterns, and the Sun seems like the anchor, bright and steady in the same patch of sky. That feeling is a frame choice, not a cosmic fact, an agreement between our senses and a shared motion. If stillness is a local agreement, then the agreement can drift, and it can drift without warning. A train feels still when every seat, wall and window shares the same velocity. Step outside the train, and the same scene becomes a blur of speed. The Milky Way is not a backdrop painted on the sky, even though it can look like one on a clear night. It is a rotating disk of stars, gas and dust wrapped around a dense central region that glows in infrared and radio light. It also has a halo that extends far beyond the bright band we see, thin, ancient and dim. We live inside that structure, so we cannot step outside and photograph it, at least not with any camera we can build. Our view is embedded, like trying to sketch a whirlpool while you're caught in its current. The galaxy surrounds us in every direction, and the brightest parts are mixed with the nearest clutter. We infer the Milky Way's shape the way you infer a forest while standing among trees, by counting, measuring, and correcting. We map star counts, dust extinction, and the distribution of gas. Then we compare those maps across wavelengths that dust cannot block. We measure distances and motions, then reconstruct a three-dimensional model that is strong, but always a view from within. The galaxy has a disk where most stars and gas orbit in roughly the same plane, like a vast, flattened storm system. It has a central bulge that is thicker and denser than the disk, crowded with older stars and complex orbits. It has a halo of old stars and globular clusters, and a much larger halo of unseen mass that reveals itself through gravity. The bright Milky Way band is the disk seen edge-on, a luminous river broken by dark lanes. Those lanes are not empty space, but dust, fine grains of carbon and silicates that absorb visible light and scatter it away. In long exposures, the band becomes textured, with knots and rifts that hint at depth. Our location is not near the center, and that matters for perspective and for measurement. The Sun sits about 8 kiloparsecs from the galactic center, roughly 26,000 light-years, in a region of the disk sometimes described as the solar neighborhood. We are embedded in the disk, not hovering above it, so our line of sight cuts through crowded star fields. Dust lanes block optical light across long paths, so the center is hard to see directly in visible wavelengths. Infrared surveys can pierce much of that obscuration, and radio observations can pass through almost entirely, Even so, the inner galaxy is not a simple scene, because many structures overlap along the same line of sight. When people imagine the solar system, they often imagine a tidy diagram with the sun at rest and planets tracing perfect rings. In reality, the sun is orbiting the galactic center like any other star, and the solar system is a set of nested orbits carried along by that larger orbit. The calm of a year hides a far larger journey, and the comfort of repetition hides translation. The sun's main motion around the galaxy is fast by any human standard, even if it is typical for stars at our radius. The circular speed near the sun is about 220 to 240 kilometers per second, often quoted near 230 kilometers per second, and it reflects how the local disk rotates around the center. It is not a single universal number, and it depends on the Milky Way's mass distribution and on how we define the center. That speed is not measured by watching the sun trace a line against a fixed background, because the background is also moving. It is inferred from the motions of many objects, from the geometry of our position, and from the way velocities change across the sky. The result is robust, but it is not a simple stopwatch reading. This is where reference frames return, sharper than before, because the word rest becomes a tool rather than a claim. Astronomers define a practical baseline called the local standard of rest, which is an average motion of nearby stars on nearly circular orbits. It is not absolute rest, but it is a useful local frame, stable enough to subtract and honest enough to admit its limits. Relative to that local standard, the sun has a smaller extra drift called peculiar velocity, which is a difference vector rather than a single speed. It is not one speed in one direction, but components in 3 dimensions, often expressed as u, v, and w, relative to the galaxy's radial, tangential, and vertical directions. Typical values are on the order of 10 to 20 kilometers per second per component, and the exact numbers depend on the adopted standard and the data set. Those components matter because they tell a story about our neighborhood's dynamics, not just our own motion. Nearby stars are not perfectly ordered, and the disk has a kind of kinetic temperature that reflects past gravitational stirring. The sun's peculiar motion is partly a personal history, and partly a signature of the disk's collective agitation, so our motion is already layered inside the galaxy's own flow, like currents inside a larger current. There is the broad orbital motion around the galactic center near 230 kilometers per second, and there is the sun's peculiar motion relative to nearby stars, tens of kilometers per second in total. Then there are the planets orbiting the sun, and Earth orbiting within that, and the stack keeps growing until the word rest keeps shrinking. The central question tightens as the frames multiply, and it becomes harder to answer with one comforting number. If we are moving so fast, why does the universe feel motionless? And why do our bodies report no acceleration? The answer remains that constant shared motion is hard to sense, while the deeper answer is that the reference points we trust are also moving. We can describe the sun's galactic orbit as a long loop, but we should not pretend it is a perfect circle traced on a clean diagram. The Milky Way's gravity field is not perfectly symmetric because spiral arms, the central bar, and local mass concentrations create perturbations. Over long times, orbits can shift and precess, and small deviations can accumulate into meaningful differences. Even the idea of orbiting the center needs careful language, because the center is a region, not a dot. The gravitational potential is distributed, and the sun responds to the combined pull of bulge, disk, and halo. What looks like a circle in a textbook becomes a rosette in a more realistic gravitational field. A single orbit around the galaxy is called a galactic year, and the phrase sounds simple until you feel its scale. It is roughly 225 to 250 million years, depending on the adopted speed and radius, and that timescale is so large it breaks intuition. It is long enough to swallow continents, climates, and entire branches of life, while the galaxy barely seems to turn. Connect that to deep time without turning it into a simple cause, because the temptation is to make a cosmic metronome. When the sun completes one galactic orbit, Earth has changed beyond recognition, with oceans rearranged and mountain ranges erased into sediment. The fossil record spans multiple galactic years, but biology is not driven by one clock, and correlations can mislead when the uncertainties are large. Still, the timescale is useful as a narrative anchor, because it gives a sense of how long the ride has been running. Dinosaurs rose and fell within a fraction of a galactic orbit, and the first flowering plants spread while the sun continued its steady rotation. Mammals diversified while the galaxy's disk carried us through changing neighborhoods, and human history occupies a thin film on that curve. The galaxy does not rush, but it never stops, and the calm is part of the illusion. If you could speed up time, the Milky Way would look less like a picture and more like weather. Stars would stream, gas would ripple, and spiral patterns would wind and loosen. Now we ask how we know the galaxy rotates, when we cannot see it from outside, and when we cannot place a marker in space that stays fixed. The method is the same as earlier chapters, but the scale forces more inference and more correction. Choose a reference that does not share the motion, measure the mismatch, and translate it into speed. And this time the witnesses are gas clouds, stars, and light itself. One key tool is the Doppler shift, the same principle used for Earth's orbital corrections, but applied to the galaxy's internal flow. When gas moves toward us, its spectral lines shift to shorter wavelengths, and when it moves away, the lines shift to longer wavelengths. Measure the shift precisely, and you get radial velocity, a speed along the line of sight. That sounds simple, but the precision is earned, because spectral lines are not perfect needles. They have widths, they can blend, and they can be affected by temperature, turbulence, and instrumental calibration. Astronomers build stable spectrographs, compare to reference lamps, and correct for Earth's own motion before they interpret the galaxy. For the Milky Way, the most famous tracer is neutral hydrogen, the most abundant element in the universe in one of its simplest forms. Hydrogen emits radio waves at a wavelength near 21 centimeters, produced by a quantum spin-flip transition that is rare for any single atom but powerful in aggregate. That line can pass through dust that blocks visible light, so it lets us map gas across the disk, including regions we cannot see optically. In visuals, this is where the galaxy becomes a radio landscape, with bright ridges and broad planes of emission. The sky map is not a photograph of stars, but a chart of gas, and the gas traces the disk's structure. The Milky Way's band becomes a thick, luminous belt, with intensity variations that hint at spiral features. By measuring 21 centimeter Doppler shifts across the sky, we build a velocity field, a kind of wind map for the galaxy. We see systematic patterns consistent with rotation around the galactic center, with different longitudes showing different radial velocities. We also see deviations from simple rotation, tied to spiral structure and local flows, and those deviations are clues rather than errors. The map is not a photograph, but it is a dynamical reconstruction, and it carries a quiet power. Each spectrum is a line of evidence, and together they form a coherent motion. The galaxy reveals itself not by posing, but by moving. Another key tool is astrometry, the measurement of star positions and their changes, which turns the sky into a grid of shifting points. Proper motion is the apparent motion of a star across the sky, measured in tiny angles per year. Radial velocity is motion along the line of sight, measured by spectroscopy, and combine them with distance and you get a three-dimensional velocity. Distance is the hinge, because without it, proper motion is only an angle. Parallax provides that hinge, using Earth's orbit as a baseline, and it is a geometric method that does not rely on how bright a star looks. Even then, parallax measurements have biases and uncertainties, and astronomers must model them carefully to avoid building a distorted galaxy. Gaia transformed this part of the story by measuring over 1 billion stars, and by doing it with a consistent instrument and a consistent scanning strategy. It tracks tiny shifts in position that accumulate over years, and those shifts are so small they feel almost philosophical. It provides parallaxes for distances and proper motions for transverse speeds, and with radial velocity surveys, Gaia turns the sky into a moving map. This is where the galaxy stops being a static picture and becomes a fluid system, full of streams and ripples. Stars stream, cluster, and disperse, and some move in coherent groups that remember their birthplaces. The disk shows patterns that hint at spiral arms and resonances, and the sun's own motion can be measured against this sea of stellar trajectories. The local standard of rest emerges from these data as a statistical average, not as a physical object you could point to. Nearby stars have random motions on top of the disk's rotation, and those random motions are not noise, but part of the galaxy's dynamical temperature. The sun's peculiar velocity is defined relative to that average, and the definition is practical rather than metaphysical. Yet even that average is not perfect, because the disk is not perfectly smooth, and the neighbourhood is not perfectly representative. Spiral arms create streaming motions that bias local samples, and the central bar can drive resonances that shape velocities far from the centre. Measurements are precise, but interpretation still requires models, and models must admit what they cannot resolve. Now the narrative introduces a more unsettling inference, one that has shaped modern astrophysics for decades. If we compute orbital speeds from visible matter alone, the numbers do not fit, and the mismatch appears in many galaxies, not just ours. In many systems, rotation curves stay flat at large radii, meaning orbital speed does not drop as quickly as expected from the luminous mass. In a simple picture, if most mass were concentrated near the centre, outer stars should orbit more slowly, because gravity would weaken with distance. The speed would decline in a predictable way, and the curve would fall like a fading echo. Observations often show something closer to constant speed across large radii, and the mismatch is not subtle. Historically, this problem did not arrive as a single dramatic revelation, but as a pattern that refused to go away. Early measurements of galaxy rotation hinted at extra mass, and later surveys made the case harder to dismiss. By the late 20th century, the flatness of rotation curves had become a recurring demand for unseen gravity. This is where dark matter enters the story, not as a myth, but as a bookkeeping demand imposed by motion. Dark means non-luminous, not necessarily supernatural, and it does not emit or absorb light in the usual ways. We infer it from gravity, from what motions require, and from how structures grow in the universe. For the Milky Way, dark matter is part of the explanation for our orbital speed near 230 km per second, especially at our distance from the centre. The visible disk and bulge contribute, but not enough to hold the outer rotation at observed values, and a massive halo of unseen matter provides extra gravitational pull. The halo is not a decorative add-on, but a structural component in current models, shaping the galaxy's stability and its long-term evolution. We should be careful about what is known and what is not, because the word dark can invite careless mystery. Dark matter is strongly supported by multiple lines of evidence, including galaxy rotation, gravitational lensing, and cosmic structure formation, and those lines reinforce one another. Its particle nature remains unknown, and that uncertainty matters, because the gravity is measured but the substance is inferred. The effect on our story is psychological as much as physical, because it changes what we think we're riding through. We're not only moving fast, we're moving through a gravitational landscape partly shaped by something we cannot see. The galaxy's path is guided by visible stars and invisible mass together, and the reference points dissolve further because even the map's scaffolding is partly dark. Now return to the solar system's local environment inside the disk, because the Milky Way is structured, and we travel through that structure. Spiral arms are regions of higher density, rich in gas and star formation, where massive blue stars burn briefly and die violently. They are not rigid arms like spokes, but patterns that stars and gas move through, like traffic waves on a crowded highway. In visuals, spiral structure is best shown as a density enhancement, not as a solid ribbon. Gas compresses as it enters the pattern, molecular clouds form, and star-forming regions light up in ultraviolet and infrared. Then the gas moves on, and the pattern persists as a wave rather than a permanent set of objects. As the Sun orbits, it may pass near or through spiral features over long times, and those passages can change the local density of gas and the rate of nearby supernovae. They can perturb comet reservoirs through gravitational tides and stellar encounters, nudging long-period comets toward the inner solar system. The timing and strength of these effects are uncertain, and we should not claim simple biological triggers, but the mechanisms are physically plausible. Molecular clouds add another layer of local hazard and uncertainty, because they are massive and cold and not evenly distributed. These are dense regions of gas and dust where stars form, and they can contain enough mass to tug on passing systems. Passing near a massive cloud could perturb the outer solar system, and it could also change the interstellar environment around the heliosphere, altering how our bubble of solar wind interacts with the galaxy. That boundary matters because it is a shield of sorts, though not an absolute one. The heliosphere deflects many charged particles, and its size depends on the pressure of the surrounding interstellar medium. If the Sun moves into a denser region, the heliosphere can compress, and that could change the flux of cosmic rays that reach the inner solar system. There is also motion perpendicular to the disk that complicates the simple orbit picture. and it is easy to forget because most diagrams are flat. The Sun does not stay exactly in the galactic plane, but oscillates up and down through the disk as it orbits the centre. The period is often estimated on the order of tens of millions of years, but values vary by model and by the assumed mass density near the plane. This vertical oscillation is conceptually important even if the details are debated, because it makes the trajectory three-dimensional. It means our path is not a flat circle drawn on a map, but a wave through a layered medium of stars, gas and dust. The solar system is not just going around, it is bobbing through the plane, crossing regions where density and radiation fields can differ. Crossing the plane could correlate with changes in local density and radiation environment, but it could also be dynamically mild depending on the actual density profile and our vertical amplitude. The evidence does not support a single dramatic cycle that dictates Earth's fate, and the honest story is that the environment changes while the causal chain is complex. If we want to connect sky motion to life, we must do it with humility and with error bars. Now we pull back and name the emotional shift this chapter is meant to create, because the science changes the feeling of home. In earlier layers, the Sun felt like an anchor, a stable centre that made the rest of the sky make sense. Here, the Sun becomes another passenger, and the galaxy becomes the vehicle, and the vehicle itself is not still. Home becomes a moving coordinate system, and the coordinate system is not fixed, which is both elegant and unsettling. The method of measurement becomes part of the mystery, because we only know the ride by subtracting motions we share. We measure Doppler shifts in gas and infer rotation from systematic patterns, and we measure proper motions and parallaxes to reconstruct velocities in 3 dimensions. We average nearby stars to define a local standard of rest, then measure the Sun's peculiar drift, and we do it with careful statistics. Each step is powerful, but each step depends on assumptions and corrections, and the corrections are part of the truth. Distances have uncertainties that propagate into velocities, dust biases which stars we can see, and non-circular motions complicate the cleanest models. The galaxy is measurable, but it is not simple, and the complexity is not a flaw in the story, it is the story. The Milky Way is a living gravitational system shaped by past mergers, ongoing star formation, and the slow redistribution of angular momentum. This is also where the documentary's theme of subtraction returns, because subtraction is how motion becomes visible. To detect small signals, we subtract large known motions, and to define a stable frame, we average over many moving objects. The more we measure, the more we learn that stability is constructed, and stillness is an engineered approximation. Now quantify the scale again to keep momentum, because numbers can shock the imagination into attention. At roughly 230 kilometers per second, the Sun travels about 230 kilometers every second around the galaxy, and the distance accumulates with ruthless smoothness. In 1 minute it moves about 13,800 kilometers, farther than Earth's diameter, and in 1 hour it moves about 828,000 kilometers, more than twice the distance to the Moon. In 1 day, that becomes about 19.9 million kilometers of galactic arc, and the curve is so gentle we cannot feel it. In 1 year it is billions of kilometers, and the number stops being intuitive because our minds are not built for that scale. Yet the motion is smooth enough that the body reports nothing, and the universe remains quiet because the ride is shared. The solar system's internal orbits ride on top of this motion like gears on a moving platform, adding and subtracting depending on direction. Earth's 30 kilometers per second around the Sun adds vectorially to the Sun's galactic motion, and sometimes it adds while sometimes it subtracts. The combined velocity relative to a chosen frame changes through the year, and that changing vector is what precision astronomy must correct. This is why the question of how fast are we moving always demands a reference, even when the question sounds absolute. Relative to Earth's surface, you are nearly at rest, aside from the turning of the planet beneath your feet. Relative to the Sun, you are moving at tens of kilometers per second, and relative to the local standard of rest, the solar system is moving at hundreds of kilometers per second with a smaller peculiar drift. The answer is not one number, because the universe offers no final flaw and no privileged stillness. Even when we reach for the largest frames we can name, we find motion inside them. The best we can do is choose a frame that fits the question, then state the choice out loud. Now we address a common misunderstanding that can derail the story, because popular images can be misleading even when they are well-intentioned. The Sun is not dragging the planets through space like a boat towing a wake, and the planets are not passive cargo. Gravity binds the system, but the motion is mutual. and the solar system has a barycenter, a center of mass that can lie outside the Sun's surface. The Sun wobbles due to the planets, especially Jupiter and Saturn, and that wobble is measurable as a subtle reflex motion. In exoplanet astronomy, the same principle reveals planets around other stars, because the star's spectrum shifts as it moves. Even our local center is not perfectly centered, and the idea of a single immovable hub dissolves again. So the solar system's trajectory through the Milky Way is not a single line traced by a rigid object, but a bundle of paths around a shifting barycenter. It is carried by a star moving in a complex gravitational field, and the field itself is shaped by visible and dark matter together. The shape is often drawn as a helix in popular graphics, but the key truth is simpler. The whole system is translating while its parts orbit. Now return to the Milky Way's structure, because it shapes the trajectory we are describing, and it shapes the measurements we trust. The disk contains spiral patterns, gas lanes, and star-forming regions that light up in different wavelengths. The bulge and bar dominate the inner galaxy's dynamics, and they can funnel gas inward and reshape stellar orbits through resonances. The halo extends far out, and it is where much dark matter is thought to reside, but it also contains sparse stellar populations. Globular clusters orbit there like ancient lanterns, compact and old, carrying chemical signatures from the early galaxy. Their motions help constrain the mass distribution, because they respond to the same gravitational potential that guides the Sun. The galactic center itself is a special region, but we do not need to linger on it here, because the chapter's focus is the ride rather than the destination. It hosts a supermassive black hole, and it anchors the galaxy's potential well, but the well is broader than the black hole. Our orbit is far from that center, but still controlled by its mass distribution, and the center is not a point we orbit like a bead on a wire. Now we clarify why we cannot simply take a picture of the Milky Way's spiral arms, even though we can photograph other galaxies with ease. We are inside the disk, looking through dust and crowded starfields, and our view is like trying to map a city while standing in its traffic. We rely on infrared and radio surveys to see through dust, and we rely on distances and velocities to infer geometry. The reconstruction is one of science's quiet triumphs, because it turns line-of-sight measurements into a coherent model. It combines sky position, spectrum, parallax, and proper motion into a single dynamical picture. It also reminds us that knowledge is not the same as direct sight, and we know the galaxy's rotation because the data demand it. Now the chapter's mysterious tone deepens into a specific unease, because even the galaxy's rotation is not a single, rigid motion. The Milky Way is not a solid disk with one rotation rate, and different radii rotate at different angular speeds. The disk shears and patterns emerge and dissolve, and the Sun's orbit is stable enough to define a galactic year, but the galaxy is not a clock. This matters for the central question, because it undermines the idea of a universal reference that everything shares. Even the local standard of rest is local, and it is statistical, and it can shift as we change the sample of stars. The galaxy's own internal motion means there is no single galactic rest that everything shares, and rest is always a choice guided by what you want to measure. Now we connect back to the earlier chapters to maintain continuity, because the method scales even as the comfort fades. In Chapter 2, we used inertia to expose Earth's rotation, and in Chapter 3 we use light and geometry to expose Earth's orbit. Here, we use the same logic at a larger scale, with more uncertainty and more inference, and the method scales but the comfort does not. We should also state what our measurements fail to reveal, because it is easy to smuggle in an absolute claim without noticing. They do not give an absolute velocity through space in any final sense, and they do not reveal a universal background that defines true rest. They give velocities relative to chosen frames like the local standard of rest, and they give a model of the Milky Way's rotation, not a God's eye view. They reveal dark matter's gravitational role, not its identity, and that distinction matters. They reveal a structured environment, not a simple cause and effect script for Earth's history. The map is powerful, but it is not omniscient. Now bring the local environment back in, because it grounds the abstraction in physical interactions. The solar system moves through regions of varying density and radiation, and the heliosphere interacts with the interstellar medium at its boundary. Cosmic rays, dust, and magnetic fields vary with environment, and those changes are real even when their Earth impacts are hard to isolate. Spiral arm passages are often invoked in popular stories about extinctions and climate shifts, because the idea is dramatic and the timescales are tempting. The honest version is more cautious, because the timing of spiral structure, the Sun's exact path, and Earth's geological record all have uncertainties. It is plausible that environment matters, but simplistic one-to-one claims do not survive scrutiny, and the universe rarely offers a single lever. Still, the larger point holds even without dramatic claims, and it is the point this chapter wants you to feel. Our trajectory is not through empty, uniform space, but through a structured galaxy with gradients, clouds, and waves. The solar system's path is shaped by gravity from both luminous and dark matter, and the ride is smooth, but the environment is not constant. Now we pivot toward the chapter's transition, because the stack must keep climbing and the frames must keep receding. If the Milky Way is rotating internally, it is also moving externally, and the galaxy is not fixed in the universe any more than the Sun is fixed in the galaxy. The reference points keep sliding outward, and each new layer feels like the last layer's ground dissolving. The next layer is motion among galaxies, within groups and clusters, where gravity writes on even larger scales. The Milky Way and Andromeda are moving toward each other, and the local group moves relative to larger structures that trace a cosmic web. The question becomes not only how fast we move, but what we can meaningfully move relative to, when every reference is also in motion. This is the chapter's closing beat, and it returns to the documentary's conclusion theme with a colder clarity. The terrifying reality is not that we are moving fast, but that stillness was never a universal state at all. It was a local agreement inside a galaxy that is itself in motion, guided partly by matter we cannot see. Now widen the scale again without leaving the room. The Milky Way is not the final frame, and it never was. It is the next moving platform under our feet, and it is already drifting into a larger dark. The Milky Way never travelled alone, and it never travelled in silence. It moves as part of a small bound family called the local group, an island of mutual gravity embedded in a much larger expanding sea. In earlier chapters, we learned a rule that keeps returning, even when the scenery changes. Shared steady motion feels like stillness, until a larger frame exposes the drift. The trick is not that motion disappears, but that our reference point quietly moves with us. The local group is dominated by two spirals, and the balance is not subtle. The Milky Way and Andromeda hold most of the mass, with dozens of smaller satellites scattered like sparks around two larger fires. Some satellites are faint dwarf spheroidals, barely holding onto their own stars, while others still show gas and ongoing star formation. Their motion is not ruled by cosmic expansion at this scale, and that statement has a precise meaning. Gravity wins locally, and the system remains gravitationally bound because its internal binding energy exceeds the gentle outward push of the Hubble flow. In practical terms, the galaxies are close enough that their mutual attraction overwhelms the average stretching of space. Andromeda is approaching at roughly 110 kilometers per second, and the number lands with a physical weight. It is a Doppler shift turned into a closing speed, measured from the blue shift of its spectral lines as they slide towards shorter wavelengths. The signal is clean enough that it has become a staple of astronomy lectures, an approaching galaxy in an expanding universe. This is not a contradiction of an expanding universe, and the distinction matters for the rest of the chapter. Expansion describes the average stretching of space across large, nearly uniform volumes, while gravity can still pull nearby structures together into bound systems. The universe can expand overall while local neighborhoods collapse, orbit, and merge. The local group has its own internal choreography, and it is more like a slow dance than a collision course. The Milky Way and Andromeda fall toward a shared center of mass, while smaller galaxies orbit, scatter, and sometimes get torn apart by tidal forces. Long, faint stellar streams, remnants of disrupted dwarfs, trace those past encounters like chalk lines across the halo. The key idea is scale, and scale is not just distance, but time. At small enough separations, binding energy beats expansion, and the Hubble flow never fully takes over. Over billions of years, even modest gravitational tugs accumulate, turning tiny accelerations into decisive rearrangements. At larger distances, the story flips, and the flip is statistical rather than absolute. Beyond bound groups and clusters, galaxies separate on average because space itself expands between them. The farther you look, the more the expansion term dominates, and the more recession becomes the default expectation. So our motion has two components at once. and the combination can be confusing until you name it. There is the general expansion, and there is the local gravitational drift through the expanding background. The same galaxy can be carried outward by expansion, while also sliding sideways or even inward relative to that smooth trend. Astronomers give this drift a name because naming it makes it measurable. It is peculiar velocity, meaning motion relative to the smooth Hubble flow. Peculiar does not mean strange in a casual sense. It means specific to local conditions, the way a local wind differs from the planet's overall circulation. The Hubble flow is the baseline, and it is built from a simple proportionality. It is the recession speed expected from distance alone, if the universe were perfectly uniform and the only effect were expansion. In that idealized picture, doubling distance doubles recession speed, and the scatter would be minimal. Peculiar velocity is the residual after subtraction, and residuals are where structure hides. It is the part caused by nearby mass concentrations tugging on galaxies like currents, creating coherent drifts across regions that can span tens or even hundreds of millions of light years. If you want to know where the mass is, you watch how the tracers move. This is where the documentary becomes truly cosmic. We stop thinking in isolated orbits and start thinking in flows. The visual language changes too, less like planets around a star and more like weather patterns on a map. Galaxies move like leaves in a dark river, and the metaphor is not just poetic. The riverbed is gravity, shaped by mass we can map only indirectly, and the water's surface is the luminous universe we can photograph. When the current bends, it is because the bed beneath it changes depth. To see the flow, astronomers need two measurements for each galaxy, and neither comes for free. They need redshift for total recession and an independent distance estimate that does not assume the redshift is purely expansion. Without both, you cannot separate the river's current from the river's overall downstream motion. Redshift alone mixes two effects, and that mixture is the central observational trap. It includes expansion-driven recession plus Doppler motion from local gravitational pulls. In a dense region, those Doppler terms can be hundreds of kilometers per second, large enough to mimic a significant change in distance. Distance is the separator, and it is the fragile rung in the ladder. If you know how far a galaxy really is, you can predict its Hubble recession and isolate the leftover drift. The difference between predicted and observed velocity becomes a direct clue to the gravitational landscape. This is observationally brutal, and the brutality is mathematical as well as practical. Distances are hard, and errors can masquerade as flows if you're not careful, because a small fractional distance mistake becomes a large velocity mistake once you multiply by the Hubble constant. A map of currents can appear where none exists simply because the ruler was bent. The distance ladder becomes a motion detector, and that phrase is literal. It turns brightness, rotation, and standard candles into a three-dimensional velocity map, where each galaxy carries a small arrow showing how it deviates from the expected expansion. When enough arrows align, the alignment becomes a discovery. One workhorse method is the Tully-Fisher relation, and it rests on the physics of rotating disks. Spiral galaxies with faster rotation are intrinsically brighter, so rotation becomes a distance proxy once you calibrate the relation locally. The rotation speed is measured from the width of spectral lines, often the 21 centimeter line of neutral hydrogen, which traces the galaxy's outer disk. The relation is not magic, and it has scatter for real reasons. Star formation history, dust within the galaxy, and subtle differences in mass-to-light ratio all introduce noise. Yet across large samples, the statistics become powerful, and the average trend holds well enough to chart motion. Another anchor is Type Ia supernovae, and their value comes from their uniformity after correction. Their peak brightness is standardized after calibration, so they act as bright beacons across large volumes. The underlying event is a thermonuclear explosion of a white dwarf in a binary system, and the physics produces a characteristic light curve that can be stretched to refine the luminosity estimate. Supernovae are rare, which is both their weakness and their strength. You cannot place them wherever you want, but when one appears, it can be seen across enormous distances with high signal. In the nearby universe, a handful of well-measured events can anchor the scale for entire surveys. With redshifts and distances, astronomers build peculiar velocity catalogues, and catalogues become atlases of motion. They look for coherent patterns that persist beyond random scatter, and they test whether those patterns survive different calibrations and different selection cuts. A real flow should not vanish when you slightly change the sample. Those patterns reveal structure, and the revelation is almost unsettling. Galaxies do not drift randomly, because mass is not spread evenly through space. The universe is not a uniform fog of matter, it is a textured landscape. Matter forms a cosmic web, and the phrase describes both geometry and history. It is a network of filaments, nodes, and voids that emerges from gravity acting on early density ripples. Those ripples were tiny variations in the young universe, amplified over time as denser regions pulled in more material. Filaments are elongated bridges of galaxies and dark matter, and they are often the highways of infall. Nodes are dense intersections that grow into clusters and superclusters, where hundreds or thousands of galaxies share a common gravitational well. In deep images, you can almost feel the architecture, bright knots connected by faint chains. Voids are the opposite, and their emptiness is an active part of the story. They are vast underdense regions where fewer galaxies form, and where the flow tends to stream outward as surrounding matter evacuates the interior. The edges of voids can be sharp in maps, like shorelines around a dark ocean. The cosmic web is not just a picture, and not just a classification scheme. It is a dynamical map, because the same structure that hosts galaxies also accelerates them. If you could speed up time, the web would look alive, with material sliding along filaments and draining into nodes. Our local group sits inside this web, and the placement is specific even if it is not special. We're not at a centre, but we are inside a particular set of filaments and nearby nodes, and those neighbours leave fingerprints in our velocity. The sky is not an even backdrop. It is a directional field. The nearest major node is the Virgo cluster, and it is both familiar and formidable. It is a dense cluster of galaxies roughly tens of millions of light-years away, and it matters gravitationally because its mass is enormous. In wide-field views, Virgo is a crowded swarm, with elliptical galaxies dominating the core and spirals more common in the outskirts. Virgo is not just a landmark, and not just a pretty patch of sky. It is a mass concentration that contributes to our peculiar velocity, pulling our region through the local web. Even if the pull is gentle, it acts continuously, and continuous forces reshape trajectories over cosmic time. From clusters, we step up to superclusters, and the step changes the definition of what an object is. These are not tightly bound objects like a galaxy, but large-scale associations traced by flows and by the distribution of clusters. Their boundaries are fuzzy because gravity's influence fades gradually, not abruptly. A modern framing calls our home supercluster Laniakea, and the name carries a deliberate emphasis. It is defined by the basin of attraction in the local velocity field, meaning the region whose galaxies tend to flow toward a common gravitational low point. The definition is kinematic, not merely visual. Laniakea is not a rigid structure with a hard edge, and that softness is the point. It is a region where galaxy motions converge toward a common gravitational low point, while neighbouring regions drain toward different basins. In a map, the borders look like watersheds on Earth, lines where the direction of flow changes. This definition is important, and it subtly rewrites how we talk about the universe. It shifts the story from what we see in light to what we infer from motion. A galaxy's brightness tells you where it is, but its drift tells you what is pulling on it. When astronomers map Laniakea, they see streams, and the streams are visualizable even in the mind. Galaxies appear to flow along filaments toward dense regions, like drainage patterns after heavy rain. The arrows in the velocity field point inward, then curve, then merge, as if guided by invisible channels. And then a deeper mystery appears, and it arrives as a directional insistence. The flow seems to point toward something massive, in a direction that is hard to observe. The arrows do not just converge toward Virgo, they continue, as though the river bends toward a hidden valley. This is the Great Attractor, and the name is both evocative and cautious. It is not a single object, but an inferred gravitational pull revealed by coherent galaxy motions. The Attractor is a region of overdensity, a broad gravitational depression in the local potential field. The Great Attractor entered astronomy in the late 1970s and 1980s, when the tools finally allowed the question to be asked clearly. Flow studies showed that many galaxies shared a bulk motion not explained by simple expansion. Researchers compared redshifts and distance estimates, and found a persistent drift, as if the local universe were sliding. The evidence was statistical and unsettling, because it suggested a large-scale drift of our region relative to the Hubble flow. It was not just one galaxy behaving oddly, but many galaxies in different directions sharing a similar velocity component. In science, coherence across independent targets is often the first sign of a real underlying cause. The approximate direction lies toward the Centaurus and Norma constellations, and the sky location matters as much as the physics. It is a region of sky near the plane of the Milky Way, where our own galaxy's disk cuts across the background like a luminous scar. The very place we need to see is the place we see worst. That location creates the central observational problem, and it is almost cruel. The Milky Way blocks our view with dust and dense star fields, and the obstruction is not uniform. Dark lanes of interstellar dust absorb visible light, while countless foreground stars crowd the image, making background galaxies difficult to identify. Astronomers call this the zone of avoidance, and the name is a confession of limitation. In visible light, it's a band where external galaxies are hard to detect and harder to characterize. Catalogues that look complete elsewhere become patchy here, as if the universe itself had a missing strip. So the Great Attractor is partly hidden behind our own galaxy, and the irony is sharp. Our best local reference is also our biggest blindfold, because we must look through our own disk to map the structures that influence our motion. The observer is embedded inside the obstacle. Radio and infrared surveys help pierce the dust, and the shift in wavelength changes what is possible. Neutral hydrogen mapping and infrared galaxy counts can reveal structures that optical surveys miss. The 21 centimeter line, in particular, can pass through dust and trace gas-rich galaxies that would otherwise be invisible. Even with those tools, the region is messy, and the mess has consequences. Confusion from foreground stars and extinction corrections can bias catalogues and distances, and biases can masquerade as flows. A faint galaxy might be mismeasured, or missed entirely, and the missing data can tilt the inferred gravitational field. So the Great Attractor becomes a mystery object by method, not by mythology. It is a gravitational inference built from incomplete sightlines, where the strongest pull may lie behind the thickest curtain. The name persists because the inference persists, even as the details evolve. The documentary's central question returns with new force, and it becomes harder to answer cleanly. If motion is always relative, what frame are we really moving against at these scales? The deeper we go, the more every frame seems provisional. At the local group scale, the frame is practical, and it is almost mechanical. We can define a barycenter and measure velocities of member galaxies around it. The barycenter is a weighted balance point, and it shifts depending on how much mass each galaxy contributes, including the mass we infer from dark matter halos. At the supercluster scale, the frame becomes statistical, and statistics bring their own uncertainty. We define a smooth Hubble expansion and measure deviations as peculiar velocities. The smooth flow is an average over many directions, and local lumps and voids guarantee that no small patch is perfectly smooth. At the Great Attractor scale, the frame becomes contested, and disagreement becomes part of the plot. Different surveys and methods can produce different flow vectors and amplitudes. The differences do not always mean someone is wrong, because the sky coverage, the distance indicators, and the corrections can vary in subtle ways. The evidence chain starts with redshift surveys, and redshift surveys are a triumph of patient accumulation. They map galaxy positions in 3 dimensions, turning the sky into a lumpy distribution of matter traces. Each spectrum is a data point, and millions of spectra become a sculpted volume. Redshift surveys reveal filaments and walls, and the walls can be enormous. They also reveal voids and the overall anisotropy of nearby large-scale structure. In visualizations, the universe looks like a foam of emptiness with bright ridges, and those ridges are where gravity has gathered matter. But redshift space has distortions, and the distortions are not a nuisance but a diagnostic. Peculiar velocities themselves stretch and compress structures along the line of sight, creating fingers and pancakes. Clusters can look elongated because galaxies inside them have large random velocities, while coherent infall can flatten structures in redshift space. So astronomers model those distortions, and modeling is where theory meets measurement. They try to reconstruct real space density fields from redshift space maps. The goal is to infer where matter truly sits, not merely where it appears after velocity effects shift the redshifts. Then distances enter again, and the ladder returns to center stage. Tully, Fisher distances, supernova distances, and other indicators provide the independent scale needed for peculiar velocities. Each distance estimate is a bet against the simplicity of redshift-only mapping. Each indicator has scatter, and scatter is not merely random noise. That scatter propagates into velocity errors, and velocity errors can mimic bulk flows if selection effects are not controlled. If a survey preferentially includes brighter galaxies at larger distances, the inferred distances can be biased, and the bias can look like a coherent motion. So the field learned caution, and the caution was earned through reanalysis. Malmquist bias, calibration drift, and inhomogeneous sampling can all create false motion signals. A flow map can be a mirror of the survey design unless the analysis is disciplined. Despite the pitfalls, a coherent picture emerged, and it is anchored by multiple lines of evidence. Our region shows a bulk flow relative to the CMB frame, and it is not tiny. The motion is large enough to be measured in the dipole anisotropy of the cosmic microwave background, and it is also echoed in galaxy velocity studies. The Great Attractor region contributes strongly, and it appears as a nearby gravitational influence shaping the flow within Laniakea. It is part of the reason the arrows in the velocity field lean in a particular direction. Yet even this influence is not isolated, because gravity adds and the universe is crowded. Yet the Great Attractor is not the end of the river, and that is where the tension deepens. When astronomers extend the map, they find additional pools beyond it. The flow does not simply stop at the first major overdensity, because the gravitational potential is shaped by structure on many scales. One major candidate is the Shapley concentration, and its reputation is well earned. It is a massive supercluster complex farther away, and it can tug on large volumes. In the hierarchy of nearby structures, Shapley is one of the heavyweight regions, and its pull can add to or redirect the local drift. This complicates the narrative in a productive way, because it forces us to think in superposition. The flow we measure may be the sum of multiple attractors at different distances. A nearby overdensity can dominate locally, while a more distant but more massive structure can influence the broader region. It also complicates the word attractor, and language matters when the physics is distributed. The flow does not necessarily converge to a single point, because the density field is spread across filaments and clusters. A river can be guided by a whole valley, not just one sinkhole. In a web, gravity is not a single hook. It is a landscape of slopes, and galaxies respond to the combined gradient. The direction of motion is the direction of steepest descent in the gravitational potential, and that direction can curve as the landscape changes. So why did the Great Attractor feel like a single mystery, and why did it capture the imagination? Because early data was sparse, and the zone of avoidance hid key structures. When the map has a hole, the mind tends to fill it with a single answer. As surveys improved, the picture refined, and refinement is a recurring theme in observational cosmology. The Great Attractor became associated with the Norma cluster and surrounding overdensities in that region. The mass is not a solitary monster, but a complex of clusters and filaments, partially concealed and partially revealed. But refinement did not remove the tension, and tension is what keeps the story alive. Some measurements still suggest flows that are larger than expected, or misaligned with mapped mass. When the arrows do not point where the light suggests they should, the universe is hinting that something is missing. That mismatch is where the unseen forces theme becomes literal, and it ties back to earlier chapters. Gravity can come from matter that does not shine. The luminous universe is not the whole inventory of mass, and the difference is not small. Dark matter is already part of our earlier story, and it remains the quiet protagonist here. It explains flat galaxy rotation curves, and it shapes the Milky Way's halo. Without dark matter, the outer parts of galaxies would not rotate as fast as they do, and clusters would not hold together as tightly as they appear to. On these scales, dark matter is the scaffolding of the cosmic web, and the metaphor is accurate. Galaxies are luminous traces embedded in a much larger dark distribution. Where the dark matter forms a filament, gas can cool and form stars, and a visible chain of galaxies appears along an invisible backbone. So an attractor could be partly dark and partly hidden for mundane reasons. It could be a concentration of mass with fewer bright galaxies, or one obscured by dust and confusion. The gravitational field does not care whether the mass is glamorous, only whether it is there. Astronomers test this with independent mass mapping, because inference demands cross-checks. Gravitational lensing can measure mass directly through its bending of background light. The effect is a prediction of general relativity, and it turns the universe into a natural optical experiment. Weak lensing is subtle, and subtlety requires scale. It uses tiny, coherent distortions in many background galaxy shapes to infer the foreground mass field. No single galaxy image proves the case, but a statistical pattern across thousands can reveal the presence of a massive structure. Lensing does not care whether mass emits light, and that indifference is its power. It responds to total mass, luminous plus dark, and it provides a check on flow-based inferences. If velocities suggest a pull, lensing can ask whether the mass is truly there. In the nearby universe, lensing is harder than in deep surveys, and the difficulty is practical. The signals are smaller and the sky coverage must be large, and foreground contamination can complicate shape measurements. Yet the principle still matters, because it offers a way to weigh what we cannot see. Still, the principle matters for the documentary because it reinforces a larger theme. There are multiple ways to weigh the universe, and they do not all rely on brightness. Motion, light, and lensing become three different languages describing the same underlying mass field. So the Great Attractor is a lesson in method, and method is part of the mystery. We infer mass from motion, then test mass with lensing, then revise the flow model again. Each iteration sharpens the map, but each also reveals where the map remains uncertain. The uncertainties are not a weakness to hide, and they should not be edited out for comfort. They are part of the terrifying reality, because our motion is measurable yet never fully pinned down. The universe allows measurement, but it does not grant perfect vantage points. We can measure redshifts with exquisite precision, and modern spectroscopy makes that almost routine. We can measure distances with improving accuracy, but distance remains the fragile link. A small systematic offset in a distance scale can tilt an entire velocity field. We can map galaxies across huge volumes, and the maps are breathtaking in their reach. Yet the map is incomplete where our own galaxy blocks the view, and that incompleteness matters. A missing wedge in the sky can translate into an ambiguous mass distribution in the reconstruction. So we live inside a partial survey of our own river, and the perspective is inherently local. We are trying to infer the river's pull while floating inside its current. The current is not an abstraction, because it is our own velocity through the cosmos. This is where the narrative stakes escalate, and the stakes are scientific as well as philosophical. If our local supercluster is flowing, then our velocity is not just a number, but a clue. It is a clue that can be compared across methods, across wavelengths, and across independent datasets. It is a clue to the universe's hidden mass distribution, and hidden here means both dark and obscured. It is a clue to how structure formed and how gravity organizes matter. It is also a clue to the strength of the standard cosmological model, which predicts how large such flows should be on different scales. It is also a clue to what we cannot see, and the clue grows sharper with better instruments. The more precisely we measure motion, the more clearly we see the dark scaffolding. Every improved distance calibration is like clearing sediment from a river gauge. Yet even the best reconstructions can leave residuals, and residuals are where debates live. Bulk flow measurements sometimes suggest motion that extends to surprisingly large scales. If the flow persists too far, it challenges expectations about how quickly velocities should converge to the cosmic mean. Some analyses find a flow that persists beyond the expected convergence scale, and the claim is provocative. Others find smaller flows consistent with standard cosmology, and the difference often comes down to data selection and error modeling. The same sky can tell different stories if the uncertainties are treated differently. This disagreement is not just academic, because it affects what we think the Great Attractor represents. It determines whether our local motion is fully explained by known structures or partly unexplained. In science, unexplained is not a failure, but it is an invitation. If flows are larger than expected, then either the mass distribution is more anisotropic than we think, or our measurements hide systematics. If flows are misaligned, then either unseen mass lies off the mapped filaments, or our distance indicators are biased in subtle ways. Each option points to a different kind of missing knowledge. So the Great Attractor becomes a hinge in the story, and hinges are where motion changes direction. It is where the stacked motion meets the limits of our maps. The closer we look, the more we realize that the map is not the territory, and the territory is partly hidden. We can define Laniakea as a basin, and the basin concept is powerful because it is dynamic. We can identify nearby overdensities and distant concentrations, then compute their combined pull. We can simulate how matter should flow in a universe like ours, then compare the simulated arrows to the observed ones. But we cannot yet claim a final accounting, and honesty demands that we say so. The river is wider than our nearest banks, and the far current still matters. Even beyond the Great Attractor and Shapley, the large-scale density field continues, and its integrated influence can be felt. This returns us to the documentary's hook, and the hook is psychological as much as physical. You feel still because your senses evolved for local hazards, not for cosmic gradients. Your inner ear can detect acceleration, but it cannot detect a steady drift shared by everything around you. On Earth, constant velocity hides, and the hiding is built into perception. In the local group, shared drift hides again, because every nearby galaxy shares part of the motion. The sky becomes a moving stage where the props drift together, making the drift hard to notice. Only by comparing to a larger reference can we see it, and the need for a reference becomes the narrative engine. The question becomes which reference is stable enough to serve as a cosmic baseline. Each candidate frame solves one problem while introducing another. The Hubble flow is one baseline, but it is statistical and local structure distorts it. The local group barycenter is another, but it is parochial. Both frames are useful, yet both are embedded in the very structures whose influence we are trying to measure. We need a frame that is older than galaxies and larger than superclusters, and the requirement is not poetic. We need a reference that belongs to the universe itself, not to any one region of the cosmic web. We need something that was laid down before the web matured. This is the transition to the next chapter's climax, and it is a natural escalation. To understand our motion on the largest measurable scale, we turn to the oldest light. We turn to the cosmic microwave background, the afterglow of the early universe, which gives us a practical cosmic rest frame. And when we measure our motion against that ancient light, the river of galaxies becomes a single vector. The stillness breaks again, one layer higher, and the mystery becomes sharper because the baseline is no longer local. The question is no longer only where the river bends, but why the entire river is moving at all. Relativity denies an absolute rest, and earlier chapters leaned on that discomfort, because every still frame can be outvoted by another observer's motion. Yet cosmology offers something close to a universal baseline, defined not by philosophy, but by the oldest light we can measure. It is a baseline written across the sky, and it does not care what we call ourselves. The cosmic microwave background, or CMB, is relic radiation from the early universe, a fossil light field that has been cooling and thinning for almost the entire age of time. It was released when the universe cooled enough for electrons and protons to combine into neutral atoms, a transition that changed everything about how light could travel. That epoch is called recombination, and it happened about 380,000 years after the Big Bang. Recombination is an easy word to mishear as a single instant, but it was a process that unfolded as temperature and density fell, and as the balance between ionization and neutrality shifted. In the first few 100,000 years, matter and radiation were tightly coupled, like a churning luminous fluid where photons kept colliding with charged particles. The universe was not dark, it was too bright to see through. Before recombination, the cosmos was a hot plasma that scattered light constantly, because free electrons are extremely efficient at deflecting photons through Thomson scattering. Photons could not travel far without hitting an electron, and that repeated scattering made the early universe behave like an opaque fog. If you could have looked, you would not have seen stars or galaxies because none existed yet. You would have seen a glowing wall, every direction equally bright and equally close. Then, as expansion cooled the plasma, electrons began to settle into bound states around protons, and the number of free charges dropped sharply. The fog lifted, not because the universe stopped producing light, but because light stopped being trapped. Photons began streaming freely, and the cosmos became transparent over a relatively narrow span of cosmic time. That moment is sometimes called the surface of last scattering, a phrase that sounds geometric, even though it is really a time slice. That escaping light has been travelling ever since, and cosmic expansion has stretched its wavelength the whole way, turning what was once visible and infrared radiation into microwaves. Its spectrum cooled from thousands of Kelvin to a microwave temperature of about 2.725 Kelvin today, a value measured so precisely that it reads like a laboratory constant. The CMB is not coming from a place, it is coming from a time. When we point a telescope at it, we're not aiming outward so much as aiming backward. Visually, the idea is almost impossible to hold in the mind, so the documentary leans on a simple image. Imagine the universe as a dark ocean, and imagine the CMB as a faint uniform glow embedded in the water itself, not shining from a distant shore. Every direction you turn, you intercept photons that last scattered when the universe was young, dense, and nearly featureless. The glow is everywhere because the early universe was hot everywhere. The CMB fills all of space because it is the afterglow of a universe that was once hot everywhere, and because the last scattering surface is centered on every observer. Wherever you are, you look back to the same early boundary of transparency, and that boundary forms a sphere around you. Move to another galaxy, and the sphere recenters there, because it is not a shell in space, it is a relic layer in time. In an idealized universe with no local motion, the CMB would look almost perfectly uniform, with the same temperature in every direction. That uniformity is not just aesthetic. It is a measurable condition that can be tested with instruments and statistics. It defines a practical rest frame, even if philosophy resists the word absolute. In cosmology, rest often means the frame where the universe looks most isotropic. The first and strongest pattern in the CMB is not the famous tiny mottling that later became a triumph of precision cosmology. It is a large dipole anisotropy, a simple hot side and cold side painted across the whole sky. The sky is slightly hotter in the direction we're moving, and slightly cooler behind us. It is the oldest light behaving like a wind. This dipole is interpreted as a Doppler effect, and the logic is as clean as any in observational astronomy. Motion toward the CMB blue shifts the photons and raises the measured temperature, because the spectrum is pushed to slightly higher frequencies. Motion away redshifts them and lowers the measured temperature, because the spectrum is pulled to slightly lower frequencies. The CMB is a near-perfect blackbody, so a tiny frequency shift looks like a tiny temperature shift. The dipole is not a subtle statistical claim that needs 1,000 plots to believe. It is a clear, global signal that dominates the CMB map before any fine structure is discussed, and it appears as soon as you have a stable full-sky measurement. It is the universe telling us our velocity relative to its oldest observable light. It is hard to watch that map and still pretend we have no cosmic drift. From the dipole amplitude, we infer our speed relative to the CMB rest frame, and the commonly cited value is about 370 kilometers per second, often quoted near 368 kilometers per second. The direction points roughly toward a region of sky near Leo and Crater, a patch of constellations that serve as labels on a much larger truth. The exact coordinates are less important than the fact that there is a direction at all. This is the documentary's most haunting pivot, because it compresses an entire hierarchy of motions into one arrow. We can describe a single cosmic movement vector for us, not just nested local motions inside a solar system inside a galaxy. The number is not a metaphor because it is measured from a spectrum, and because the dipole is visible before interpretation adds poetry. A single map turns "we are moving" into a quantified statement. Now, widen the scale without leaving the room. The CMB rest frame is not a denial of relativity's core rule, and it does not claim a metaphysical absolute rest that would resurrect Newton's stage. Instead, it is a physical frame singled out by the universe's history because the CMB provides a natural standard of isotropy. Relativity allows preferred frames when they arise from matter and radiation content, as long as the laws remain the same in all inertial frames. The preference is empirical, not fundamental. If you move with the Hubble flow and have no peculiar velocity, the CMB looks isotropic on average, aside from the tiny primordial ripples. If you drift through that flow, the dipole appears, and its amplitude becomes a speedometer. The rest frame is defined operationally by the condition that the dipole vanishes. In practice, rest means no dipole, and that definition can be tested and refined. This is why the CMB is so powerful as a reference, and why it keeps returning in modern cosmology like a refrain. Stars move, galaxies orbit, and superclusters flow toward overdensities, and each of those motions can be described relative to something else. The CMB is older than all of those structures, and it surrounds us in every direction with the same ancient origin. It is the closest thing we have to a universal backdrop that is not made of nearby matter. Measuring the dipole is not a single thermometer reading, and it is not done by simply pointing an antenna and writing down a number. It requires instruments stable enough to compare temperatures across the sky at microkelvin precision, because the dipole is only a few millikelvin on top of a 2.7 Kelvin background. It also requires ruthless correction for everything that is not the CMB, because the microwave sky is crowded. Every correction is a potential place for doubt to enter. The modern dipole measurement is anchored by satellite missions, because satellites can scan the full sky with stable conditions and without the atmosphere's shifting emission. COBE, the Cosmic Background Explorer, first mapped the CMB with enough fidelity to reveal its anisotropies and to confirm the blackbody spectrum with stunning accuracy. That blackbody confirmation mattered because it turned the CMB from a plausible relic into a near-inevitable one. The map refined the full sky map, improved calibration, and controlled systematics with a discipline that made the dipole and the smaller patterns mutually consistent. Planck pushed further, with higher resolution, broader frequency coverage, and deeper sensitivity, and it did so with an engineer's obsession for characterizing every instrument behavior. Multiple frequency channels matter, because the sky is contaminated by foreground emission, and the foregrounds do not politely stay in one band. The CMB must be separated from the Milky Way's dust and synchrotron radiation, and that separation is a careful act of inference. In the final maps, the clean cosmic signal is the result of subtraction as much as detection. Calibration is the quiet backbone of the result, and it is easy to underestimate how much of cosmology is metrology. Instruments must know their gain, their beam shapes, and their time response, because scanning a sky is also scanning your own imperfections. Small drifts can mimic large-scale patterns if not modelled and removed, and the dipole is itself a large-scale pattern. The irony is sharp. The most obvious anisotropy is also the one most vulnerable to slow instrumental biases, unless you are careful. Foreground subtraction is not optional, and it is never perfect, because the Milky Way is a bright microwave object when you look with the right eyes. Galactic dust emits strongly at microwave and sub-millimeter wavelengths, especially along the plane where star formation and cold clouds concentrate. Synchrotron emission, produced by relativistic electrons spiraling in magnetic fields, dominates at lower frequencies and carries a different spectral slope. Free emission from ionized gas adds another component, and point sources add still more complexity. The separation strategy is multi-frequency consistency, and it relies on a simple physical contrast. The CMB has a nearly perfect blackbody spectrum, so its brightness changes with frequency in a precisely known way. Foregrounds have different spectral shapes, so maps at different frequencies can be combined to isolate the CMB component, often using component separation algorithms that treat the sky like a mixture of known ingredients. The result is not magic. It is a controlled compromise between noise, resolution, and contamination. This is also where we clarify two different kinds of CMB structure, because they are often conflated in popular retellings. The dipole is dominated by our motion, and it is not the same as primordial anisotropies. The smaller anisotropies are the early universe's density ripples, imprinted before galaxies existed, and they are the reason the CMB became a cosmological Rosetta Stone. One pattern is about us, the other is about the universe's initial conditions. Those tiny fluctuations are the seeds of the cosmic web, and they are measured at tens to hundreds of microkelvin, a whisper on top of a uniform glow. They encode cosmological parameters, including the universe's composition, its curvature, and the relative amounts of ordinary matter, dark matter, and dark energy. They also carry the imprint of acoustic oscillations, sound waves in the early plasma that froze into a pattern of hot and cold spots. In plain language, the CMB is a snapshot of primordial vibrations, but the dipole is larger than all of that fine structure, and it sits above the primordial story like a moving shadow. It is our local kinematics written across the entire sky, and it must be removed to reveal the subtler map beneath. In that sense, it is the subtraction step that turns the CMB into a rest frame. We do not erase it because it is unimportant, but because it is too important to confuse with the universe's birthmarks. Once the dipole is measured, the story becomes layered again, because the CMB dipole reflects the net velocity of the observer. That observer is not Earth alone, but Earth inside a moving stack of reference frames, each one carrying the next. The map is telling us what the whole stack is doing, not what any single layer does in isolation. It is a cosmic sum, not a local anecdote. Earth's rotation contributes a small velocity depending on latitude and time of day, and it changes direction as the planet spins under the sky. Earth's orbit adds about 30 kilometers per second around the Sun, and it modulates the dipole slightly over the year, creating a predictable seasonal signal. The solar system's motion around the Milky Way adds roughly a few hundred kilometers per second, and it points along the galaxy's rotation, not along our ecliptic. Each component is real, and each one is measurable in other ways. Then come the local flows described in Chapter 5, where gravity organizes motion at scales far beyond a single galaxy. The local group moves relative to nearby galaxies, and our region participates in bulk motion toward nearby overdensities, including the Great Attractor direction and larger scale structure. These flows are not mystical pulls. They are the consequence of mass distributions that bend trajectories over billions of years. The cosmic web is not only a map of matter, but a map of accelerations. All of these are vectors, not scalars, which means direction matters as much as magnitude, and addition can cancel as well as compound. They add and subtract depending on direction and time, and the time dependence is why careful analyses often separate solar dipole from orbital dipole. The CMB dipole is the final sum, the net arrow after every nested motion is combined. In a sense, it is the universe doing vector bookkeeping on our behalf. This is why the universe feels motionless in daily life, even though the numbers sound enormous when spoken aloud. Most of these velocities are nearly constant over short times, and constant velocity is invisible to our bodies. Our senses detect acceleration, not steady drift, and the drift is shared by everything around us from air to oceans to the ground underfoot. The train feels still when the carriage moves smoothly, and the CMB is the landscape outside the window. Yet the CMB does not share our motion, and that is what makes it such a strange kind of reference. It is the one backdrop that does not ride with the local train, because it is not bound to the Milky Way or to the local group. It is a field of photons that has been free streaming since the universe was young, and it keeps its own memory of the cosmic average. It is the reference that makes the hidden velocity visible. If the Milky Way is rotating internally, it is also moving externally, toward other galaxies, within a larger web of cosmic structures. Now we confront a common confusion that can flatten the meaning of the number, especially when expansion and motion are spoken in the same breath. The CMB dipole measures motion through space relative to the CMB rest frame, meaning a peculiar velocity relative to the co-moving average. It does not directly measure the expansion of the universe itself, and it does not tell us how fast space is stretching. That distinction is not a technicality. It is the difference between two kinds of redshift. Expansion is described by the Hubble-Lemaitre law, a relationship discovered in the early 20th century when astronomers realized that distant galaxies are, on average, receding faster the farther away they are. On large scales, distant galaxies recede with speed proportional to distance, and that proportionality is expressed through the Hubble parameter. That recession is not shrapnel flying through static space, but space stretching between galaxies, so the geometry itself changes with time. In plain language, the ruler is growing. In that picture, a galaxy can be nearly at rest in co-moving coordinates, and still have increasing distance to other galaxies, because the coordinate grid expands with the universe. The expansion is built into the metric, not into a conventional velocity through space, and that is why naive speed limits can mislead. The language of motion becomes frame-dependent and easy to misuse, because the same observation can be described as Doppler-like or as geometric stretching. Cosmology requires a careful choice of words, but peculiar velocities ride on top of expansion, and they are the universe's local deviations from smoothness. Local gravity pulls galaxies into groups and clusters, and those gravitational flows create real Doppler motions relative to the smooth Hubble flow. A galaxy can be co-moving on average yet still fall toward a cluster, orbit within a group, or stream along a filament. The Hubble flow is the background, gravity writes the annotations. The CMB rest frame is closely tied to the co-moving frame, and that connection is why the dipole is so interpretable. A co-moving observer sees the CMB as isotropic on average, aside from primordial anisotropies. A non-co-moving observer sees the dipole, and that dipole becomes a direct measure of peculiar velocity. It is one of the rare cosmological measurements that reads like a speedometer, without too many hidden assumptions. This is the climax clean promise, and it is why the chapter's title dares to speak of a rest frame at all. We finally have a cosmic baseline that is not parochial like the local standard of rest, which depends on nearby stars and galactic conventions. We have a frame defined by the early universe itself, and we can state our speed against it. The universe gives us a reference that is older than our structures and broader than our maps. Yet the documentary's tone turns darker, because the map does not stay perfectly coherent once we look beyond the dipole. The dipole is robust, but the universe beyond the dipole is not always as tidy as the simplest model predicts, especially at the largest angles. The cracks appear where statistics are weakest and where systematics are hardest to tame, which is exactly where a mystery can hide. The most unsettling questions live at the largest scales. First, we state what is solid, because the story must keep its footing. The CMB dipole is measured with high significance, and its interpretation as Doppler motion is strongly supported by consistency across instruments and frequencies. It also matches independent expectations from local flow measurements, which track how galaxies move relative to one another. In other words, the dipole is not an isolated claim. It is stitched into a broader fabric of evidence. Historically, this confidence did not arrive overnight, and it is worth remembering how recently the CMB became a precision tool. The CMB itself was discovered in the 1960s, and its blackbody spectrum was later confirmed so well that it became one of the cleanest measurements in all of astronomy. COBE's detection of anisotropies in the early 1990s turned the CMB into a map of initial conditions, and it also forced the community to confront the sky as a full-sphere dataset. From then on, every improvement in sensitivity made the dipole and the subtler patterns more sharply separated. Then we state what is debated, without turning debate into certainty, because mystery is not the same as proof. Some analyses have reported large-scale bulk flows extending farther than expected, implying coherent motion over volumes that should have averaged out. The phrase dark flow has been used for claims of coherent motion on very large scales, often inferred indirectly through subtle effects in galaxy clusters. The name is memorable, but the inference is delicate. These claims are contested and method-sensitive, and that sensitivity is not a weakness so much as a warning label. They depend on how distances are estimated, how cluster samples are selected, and how systematics are controlled in microwave maps and in galaxy catalogues. Some studies find evidence for extended flows, while others find results consistent with standard cosmology and expected convergence. The disagreement is not about whether motion exists, but about how far coherence can persist. Another debated category is large-angle CMB anomalies, which are visually compelling because they live in the low multipoles, the broadest brushstrokes on the sky. There are reported alignments of low multipoles, sometimes called the axis of evil in popular summaries, a phrase that dramatizes what is fundamentally a statistical curiosity. There are hemispherical asymmetries and power deficits at large angular scales in some analyses, suggesting the sky is slightly lopsided in ways the simplest models did not highlight. These are not tiny spots. They are patterns that span constellations. These features are not on the same footing as the dipole, and the documentary keeps that hierarchy explicit. Their statistical significance depends on choices made after looking at the data, which is a known trap in data analysis. Foreground removal, masking, and a posteriori selection can inflate apparent anomalies, because the act of searching can create its own false certainty. Even the decision of what counts as interesting can bias the conclusion. Still, they persist as an uncomfortable set of questions, and persistence is what gives a mystery its staying power. If the universe is statistically isotropic on large scales, why do some of the largest angle patterns look oddly aligned? If inflation smoothed and randomized the early universe, why do some features look directional, as if the sky has a preferred axis? Is it a cosmic clue, or a mirror held up to our methods? We keep the distinction sharp because the narrative depends on not blurring categories. The dipole is a kinematic effect with a clear physical interpretation, and it is the dominant anisotropy by far. The higher order anomalies are subtle patterns with uncertain interpretation and ongoing debate, and they can rise or fall as analysis pipelines change. One is a measurement of our motion, the other is an argument about statistics. Even so, the emotional beat lands, because the CMB was supposed to be the cleanest cosmic backdrop, the closest thing to a universal stillness. If that backdrop shows hints of unexpected coherence beyond the dipole, then our idea of averaging out may be incomplete. or our tools may be more fragile than we like to admit. The dread does not come from a single plot. It comes from the possibility that the larger scales resist our simplifications. A background that should be featureless begins to feel watchful. Rising dread comes from a simple expectation that is built into the standard model's intuition. On very large scales, local motions should wash out as you average over more volume, because random directions cancel, and because density fluctuations become smaller relative to the mean. Bulk flows should diminish with scale in the standard model, and the convergence should be visible in surveys as you look farther out. The universe, in that view, becomes calmer when you zoom out. So why do some measurements suggest additional coherent motion on scales that should have averaged out, as if the calm never arrives? Why do some reconstructions point to flows that seem too large, or directions that seem too persistent, even when the data are thinned and averaged? If the CMB defines a rest frame, what would it mean to move coherently relative to it across enormous distances? Would it imply a large-scale gradient in the cosmic density field, or a subtle bias in how we read the sky? One possibility is mundane and painful, and science must always keep it on the table. Systematic errors can masquerade as cosmic signals, especially when the signals are low contrast and the analysis is complex. Distance indicators can be biased, selection effects can align arrows, and foregrounds can leak into maps in ways that mimic large-scale structure. The more global the claim, the more global the skepticism must be. Another possibility is that our local universe is statistically unusual but not impossible, and that the discomfort is simply the feeling of being in a rare patch. Cosmic variance allows rare patches because we only observe one universe and one sky, and the largest scales have the fewest independent modes. A large coherent flow could be a tail event rather than a new law, and a low multipole alignment could be a coincidence amplified by attention. The universe does not promise to look typical from our exact location. The most provocative possibility is that something about the largest scales is not captured by the simplest assumptions. Even if the model works brilliantly elsewhere, that does not mean the model is wrong, but it means the universe may be more structured, or our measurements more fragile than our narratives admit. The standard model is a powerful compression of reality, and compression always discards detail. The question is whether the discarded detail is merely texture or a missing term. This is where the documentary's central question sharpens into a more philosophical edge, because the CMB seems to offer an anchor and then refuses to behave like one. If we can define a practical rest frame, why does it still not feel like stillness? Why does the idea of an ultimate baseline keep dissolving, even when we find the oldest possible reference? What does it say about our intuition that even a cosmic frame feels provisional? Because the CMB rest frame is not a place you can stand, and it is not a platform floating in space. It is a condition you can approach by adjusting your velocity, and it is defined by what you see rather than where you are. It is a definition based on isotropy, not a cosmic pedestal, and isotropy is an observational criterion. The frame is real in practice, but it is not a throne, and because even in that frame, expansion continues, and the geometry keeps evolving under your feet. The universe can have a preferred comoving frame and still have no absolute rest in the older Newtonian sense, because space-time is not a fixed container. The meaning of motion depends on how you slice space-time, and different slicings can be equally valid. The CMB gives a convenient slicing, not the only one. This is where the chapter turns back on its own premise, and the narration lets the certainty curdle into something stranger. We wanted a final answer to how fast we're moving, and we found a number with terrifying clarity. Then we learned that even this number is a relative statement inside an expanding universe, and that relativity still has the last word. The universe offers a reference, but it does not offer surrender. To understand what that means, we need to separate two intuitions that our brains keep merging, because everyday language treats them as the same. Motion through space is a velocity relative to a frame, and it can be described as a Doppler shift when it affects light. Expansion is the growth of distances between comoving points, even when neither has a conventional velocity through space. One is like moving across a map, the other is like the map itself stretching. In practice, astronomers combine both ideas in one observed redshift and then spend careers disentangling them. The redshift of a galaxy includes expansion plus peculiar velocity, and the two contributions can reinforce or oppose each other depending on direction. The CMB dipole isolates our peculiar velocity relative to the comoving frame, which is why it feels like a clean subtraction. It tells us what part of our motion is not simply going with the expansion. So the CMB gives us a clean subtraction, and that subtraction is a rare gift in a field full of entangled effects. It tells us how fast our local stack is drifting through the cosmic average, and it does so with a precision that makes the number feel almost personal. It compresses Earth's spin, Earth's orbit, the Sun's galactic motion, and supercluster flows into one net vector. The sky, in effect, returns our address as a velocity. This is the climax's cold achievement, and it is hard to overstate how strange it is that we can do this at all. We can measure our motion through the universe with astonishing precision, even though we are embedded inside the system we measure. We can state a direction and a speed, and we can tie it to the oldest light we can observe, a light that predates every star. The measurement is both intimate and impersonal, but the dread is that the measurement does not grant stillness, and it never promised to, even if we secretly hoped it would. It grants only a better defined kind of motion, a clearer statement of how we drift relative to the cosmic average. It also opens the possibility that the larger scale universe is not as featureless as we hoped, or that our tools are not as clean as we imagine. The CMB becomes both a reference and a test. This is where the documentary becomes truly cosmic. We stop thinking in isolated orbits and start thinking in a universal frame that still refuses to be absolute. We end by stepping back from the number and questioning the language itself, because language is where intuition hides its assumptions. What does it mean to be moving through space, when space is stretching and when distance itself is time-dependent? What does it mean to be at rest, when rest is defined by a radiation field from a time before stars and before chemistry? Are we describing reality or describing our preferred coordinate system? The CMB rest frame is a practical answer, not a final refuge, and practicality is not the same as metaphysical closure. It is the closest thing we have to a universal baseline, because it is defined by a signal that fills the sky and comes from the same early epoch everywhere. It is also a reminder that the universe's best reference is still a relic, not a foundation. Our anchor is made of ancient photons, and photons do not hold still. Transition to the final chapter lands as a question rather than a conclusion, because the story is not finished when the number is spoken. If the oldest light can define a rest frame, and yet anomalies and flows still whisper of extra motion, then what is stillness worth? We step back and ask whether the notion collapses entirely in an expanding universe, or whether it survives as a useful approximation. The question is not only scientific, it is existential. The terrifying reality is not that we are moving fast, because speed is easy to accept when it is shared. The terrifying reality is that even when the universe offers a rest frame, it is only a local agreement with the sky, contingent on how we define average. The final rest remains out of reach, and the measurements keep pulling the floor away. The universe gives us a reference, and then reminds us that references are not absolutes. We return to the chair because the chair was never the point, and it never needed to be. The point was the feeling of stillness, how it arrives so easily, and why it survives every new speed we discover. In a quiet room, the camera lingers on ordinary surfaces, a seat cushion, a wooden armrest, dust motes suspended in a shaft of light. Nothing in the frame appears to move, yet the physics underneath it is a layered choreography. The trick is not that motion is absent, but that the motions are shared, smooth, and mostly unannounced to the body. The stacked choreography is now complete, and it must be held as layers rather than a single headline number. Earth's rotation carries you at about 465 meters per second near the equator, a speed that depends on latitude and quietly drops towards zero at the poles. That motion is mostly invisible because it is steady, circular, and shared by the floor, the air, and the walls around you. If the room had no roof, the stars would seem to wheel overhead, and the rotation would finally show itself. Historically, the proof arrived not from a rocket but from a pendulum, Foucault's pendulum swinging while the ground turns beneath it. The pendulum did not feel the rotation, but its plane of swing revealed it, slowly and inexorably, like a compass for Earth's spin. Earth's orbit adds about 30 kilometers per second, and it is not a straight line dash through emptiness. It is a constant fall around the sun, balanced by angular momentum, which is why it can feel like rest instead of flight. The orbital speed changes slightly over the year because the orbit is not perfectly circular, and yet the variation is so gentle that your nerves never register it. Even the evidence for orbit was once subtle, because the sensation is not the point. Astronomers stitched it together using aberration of starlight, annual parallax, and the clockwork of celestial mechanics. The sky itself became the instrument, and the Earth's path was inferred from tiny shifts that repeat with calendar precision. The Sun's path around the Milky Way adds roughly 230 kilometers per second, plus smaller peculiar drifts within the local disk. In wide-field visuals, the galaxy becomes a luminous band, and our position becomes a point embedded in a rotating spiral. The Sun is not centered, and it is not alone, because it travels with a cohort of nearby stars that share the disk's general flow. That galactic motion is not guessed from a single measurement, but from a convergence of methods. Doppler shifts give radial velocities, proper motions give angular drift, and Gaia turns those into a three-dimensional kinematic map with staggering detail. In that map, the Milky Way is not a static photograph. It is a dynamic system with streams, resonances, and subtle departures from perfect circularity. Beyond the galaxy, the local group and nearby web add bulk motion shaped by Virgo, Laniakea, and deeper basins. The names sound like geography, and in a sense they are, because gravity sculpts a landscape of potential wells and ridges. Galaxies drift along that terrain, and their motions carry the imprint of mass that may not shine. The net result is about 370 kilometers per second relative to the CMB, a single vector built from many. On screen, arrows stack and rotate, and then collapse into one clean direction, as if the universe allows us one moment of clarity. Yet even that clarity is conditional, because the arrow is meaningful only after we choose what rest means. This is where the documentary becomes truly cosmic. We stop asking for one speed, and we ask which frame makes the question meaningful. In everyday language, moving through space sounds like wind on your face, or the pressure of air against a hand. That intuition comes from motion relative to a surrounding medium, where friction and turbulence announce velocity. Space is not that kind of medium, and the vacuum does not provide a universal background that can be felt. In general relativity, motion is local, and free fall is the default, so constant velocity has no built-in sensation. The closest thing to stillness is an inertial frame in a small region, where gravity can be transformed away for a moment. Your body does not feel velocity. It feels proper acceleration and tidal gradients, and most of our cosmic motion produces neither. Proper acceleration is what an accelerometer reads, and it is what your inner ear translates into weight and tilt. In the chair, you feel the normal force from the floor, transmitted through the cushion into muscle and bone. That upward push is not a minor detail. It is the dominant signal your nervous system interprets as being at rest. The chair feels still because it is a local inertial compromise, stable enough to hide the larger story. Rotation and orbit are smooth enough that their accelerations are small compared to gravity, and they change slowly across human timescales. The air, the room, and your inner ear share the same motion, so there is no local reference that stays behind. Even the small non-inertial effects are muted, though they are real and measurable. Earth's rotation introduces a centrifugal term that slightly reduces effective weight at the equator, and it introduces Coriolis deflections that shape winds and ocean currents. These are not cinematic jolts, but they are persistent signatures of living on a spinning sphere. In a laboratory, the same principle becomes a precision tool. Ring laser gyroscopes and fiber optic gyros can detect rotation without looking at the sky, and inertial navigation systems can track motion by integrating tiny accelerations over time. The instruments feel what the body filters out, and they remind us that still is often a threshold of perception. Now widen the scale without leaving the room. The universe adds a second kind of change that is not a push and not a wind. Cosmic expansion is not matter rushing outward through a pre-existing emptiness, like shrapnel from an explosion. It is the metric changing, the distance between co-moving points increasing as spacetime evolves. In plain terms, the rule that converts coordinates into distances changes with time, and that is why expansion can be real without behaving like a blast. That is why expansion does not behave like a fluid flow, and why it does not produce drag. In the standard picture, co-moving observers can be at rest locally while the separation between them grows. Each observer can say, truthfully, that nearby physics looks normal, even as the large-scale geometry stretches. A helpful visual is a grid drawn on a flexible sheet. where the grid spacing increases while the ink marks remain fixed to the sheet. The marks do not move through the sheet, yet their separation increases as the sheet changes. The analogy is imperfect, but it captures the central idea. Expansion is about relationships, not about a wind. This is also why bound systems do not expand appreciably, despite the cosmic scale factor changing in the background. At small scales, electromagnetic forces bind atoms, and gravity binds planets, stars, and galaxies into stable structures. The Hubble flow is an average behavior of large, nearly uniform regions, not a force that pries apart everything. Inside a galaxy, the gravitational potential dominates over the tiny expansion rate, so the ruler does not stretch in any measurable way. The expansion rate today is roughly tens of kilometers per second per megaparsec, which sounds large until you translate it into local terms. Across the size of a solar system, the implied recession is absurdly small, far below any competing force or measurement noise. Even in intergalactic space, the story is nuanced rather than absolute. Galaxies and clusters can be gravitationally bound, orbiting a common center, while more distant galaxies participate in the Hubble flow. The universe is not divided into expanding and not expanding regions by a sharp boundary, but by a competition of scales and energies. The phrase "through space" breaks here, because space is not a rigid stage. You can ask for velocity relative to a chosen local inertial frame, and you can ask for recession due to expansion, but they are not the same quantity. Redshift can contain both, and separating them is an act of modelling rather than a single direct reading. Even the clean CMB dipole is a statement about peculiar velocity relative to a co-moving average, not a measurement of expansion itself. The dipole is a temperature anisotropy, a hot side and a cold side, produced by our motion relative to the CMB rest frame. It is a remarkably simple pattern, but its simplicity can tempt us into thinking it is a final answer. So the central question shifts. The terror is not the speed, it is the loss of a privileged viewpoint that would make one answer final. The CMB frame looked like a rescue, because it offered a practical cosmic rest that could be defined and tested. We define it operationally as the frame where the dipole vanishes, and we measure our motion as about 370 kilometers per second. That number is robust, cross-checked, and deeply informative, because it ties our local history to the early universe. The CMB itself is a relic, light released when the universe cooled enough for electrons and protons to form neutral hydrogen. Before that moment, photons scattered constantly in a hot plasma, and the universe was opaque. After recombination, the photons streamed freely, and they have been travelling ever since. Billions of years of flight, arriving now as microwaves. When we map that radiation, we're not just looking outward, we are looking back in time. The dipole sits on top of smaller anisotropies, tiny temperature variations that reflect primordial density fluctuations. Those fluctuations became the seeds of galaxies and clusters, so the CMB is both a reference frame and a fossil record. Yet even this rest is still a definition tied to what we can observe, not a metaphysical still point. If we lived in a different region of the cosmos, a local peculiar velocity could differ, and the dipole would point another way. The CMB frame is special because it is accessible and nearly universal within our horizon, not because it is written into reality as an absolute. The map breaks again when we ask what lies beyond our observational reach. The universe does not give us infinite sightlines, and it does not give us infinite time. Cosmic horizons are not a storytelling device. They're a physical limit built from light speed and cosmic history. The particle horizon marks the farthest distance from which light has had time to reach us since the beginning. The observable universe is not the whole universe. It is the part causally connected to our past light cone. On screen, the horizon is drawn as a sphere around us, but the geometry is more subtle than a simple boundary. The radius is not just how far light travels, because space itself has expanded while the light was en route. The result is a horizon measured in co-moving distance, a bookkeeping that respects the changing metric. When we speak about everything moving relative to something else, we're already speaking from inside a boundary. We can measure what reaches us, and we can model what likely exists beyond, but we cannot directly sample the whole. The word everything becomes a philosophical flourish unless we add the quiet caveat, everything we can observe. There is also an event horizon in an accelerating universe, which limits what will ever be able to affect us. Some galaxies are visible now, but their future light will never reach us if expansion accelerates enough. The universe can show you an object and still deny you its future, which is a strange kind of cosmic farewell. This is not just an abstract diagram, because it changes what questions are answerable in principle. The map of motion is time-dependent, and the accessible dataset shrinks in a practical sense. Even perfect instruments cannot observe beyond causality, because no amount of sensitivity can replace missing information. This constraint changes what claims can mean, especially on the larger scales. We can define a co-moving frame within our horizon, and we can test isotropy within our sky. We cannot verify whether the universe beyond our horizon shares that frame, or whether larger gradients exist that we will never detect. Any statement about the motion of the entire cosmos becomes conditional, because we cannot sample the whole. We can say what is consistent with what we see, and we can quantify uncertainties, but we cannot step outside the universe to check the answer. The map is drawn from within the territory, and that is an epistemic limitation, not a technical oversight. This is where cosmic variance becomes more than a technical footnote, and more like a boundary on certainty. On the larger scales, we have only one sky, and only a few independent modes to measure. Rare patterns can occur, and we cannot rerun the universe to see what is typical, so probability becomes a quiet companion to every claim. Some anomalies may be hints, some may be noise, and some may be our own analysis choices reflected back. Foregrounds from our galaxy must be modelled and subtracted, masks must be chosen, and pipelines must be validated. A small change in method can shift the significance of a large-angle feature, which is why caution is not timidity but discipline. The same limit appears in large-scale flows, where we try to measure motion using galaxies as drifting markers. We can measure peculiar velocities and infragravitational basins, but we do it with imperfect distance ladders and incomplete sky coverage. Bulk flow claims depend on calibration, selection, and how errors propagate into velocity residuals. Distance measurements are hard because the universe does not hand us rulers. We build ladders from standard candles and standardizable relations, and each rung adds scatter and systematic risk. When a distance is slightly wrong, the inferred peculiar velocity can be dramatically wrong, because it is extracted by subtracting a large Hubble recession from a noisy estimate. Some reported flows extend farther than expected, and others converge as the standard model predicts. The debate is not about whether we move, it is about how quickly the river should calm. At stake is not the existence of motion, but the statistical texture of the cosmic web on the largest accessible scales. Underneath those flows is a structure we mostly cannot see directly. Dark matter is not an optional character in this story. It is the scaffolding that makes the web. We infer dark matter from rotation curves, from cluster dynamics, from lensing, and from the growth of structure from CMB seeds. In spiral galaxies, stars orbit too fast in the outskirts for the visible mass to hold them, implying an extended halo. In clusters, galaxies move as if bound by far more mass than the luminous matter provides. Gravitational lensing adds a different kind of evidence because it uses geometry rather than dynamics. Background galaxies appear sheared and magnified, their shapes subtly aligned by intervening mass. The lensing map often extends beyond the light, showing that the gravitational potential is deeper and broader than the visible distribution suggests. On large scales, the luminous galaxies are tracers embedded in a deeper potential. The flows we measure are responses to gradients in that potential, not to the light distribution alone. That is why the Great Attractor story never reduced to one bright object, and why hidden mass can shape visible motion. Yet inference has a cost, because every reconstruction is an interpretation of limited data. Reconstructing the potential from velocities requires assumptions about bias, about the relation between galaxies and mass, and about the statistical properties of initial fluctuations. If galaxies are biased tracers, then the light-to-mass relationship shifts with environment, and the map must be corrected. Lensing can weigh mass more directly, but it has its own systematics and limited sensitivity nearby. Shape noise, intrinsic alignments, and calibration of the point spread function all matter, and they can masquerade as signal. Every method is a translation, and translations can disagree at the edges, especially where the data are thin. So we separate what we know from what we suspect, and we keep the hierarchy explicit. We know Earth rotates because Foucault and inertial navigation and atmospheric dynamics all agree. We know Earth orbits because aberration, parallax, and celestial mechanics lock together. and because the entire solar system's architecture makes sense only with that motion. We know the Sun moves around the galaxy because Doppler proper motions and Gaia's kinematic map converge. We know the CMB dipole exists, and it yields a precise net velocity relative to the comoving frame. These are not fragile conclusions because they are supported by independent lines of evidence that interlock. We suspect more than we can prove about the larger scales, and that suspicion is carefully bounded. Some flow reconstructions suggest extra coherence, and some CMB large-angle features look oddly aligned. Their significance is sensitive to masks, foreground subtraction, and a posteriori choices, which is why arguments persist even among experts. They might be physics, they might be statistics, and they might be method. If they are physics, they would hint at structure or conditions beyond the simplest assumptions of isotropy and Gaussian initial fluctuations. If they are statistics, they would remind us that rare outcomes happen somewhere, and we happen to live in one outcome. This is the edge of what we can know, and it is not a failure of effort. It is the consequence of living inside one realization of a universe with horizons. The universe gives us one dataset, and it asks us to be honest about what one dataset can support. The central question can now be answered, but the answer is a reframing rather than a final number. You feel motionless because your senses report acceleration, and most of your cosmic motion is steady free fall. You can measure astonishing speeds because physics compares frames with clocks, spectra, and geometry, but you cannot demand a final through space that is independent of coordinates, because space-time itself is part of the system. In relativity, coordinates are tools, not divine labels, and different tools highlight different features. The most honest description is the one that matches the question you are actually asking. Stillness is not a property of the universe, it is a relationship between you and a chosen reference frame. The chair is still relative to the room, and the room is still relative to the air, and those agreements are locally true. In practice, our nervous systems treat those agreements as reality, because they are stable and predictive. The closest thing to cosmic rest we can access is the CMB frame, because it minimizes large-scale anisotropy. Yet even that rest is practical, defined by a condition on a sky we can observe, and limited by the fact that our sky is only one. The CMB frame is a powerful convention, useful, measurable, and not ultimate. The unsettling comfort is that the map is real, even if it is not complete. We can stack the motions, add the vectors, and predict the modulations in the dipole across day and year. We can connect local flows to the cosmic web, and connect the web to early universe seeds, and we can test those connections against data. We can do this from a chair, using light that has crossed billions of years. The visuals widen from the room to the night sky, then to a full sky CMB map, then to a lattice of filaments and voids. The mundane and the cosmic remain stitched together, because the same physics governs both. But the universe does not grant a final here. Horizons cut the data, cosmic variance limits certainty, and dark structure forces inference. The best physics gives a coherent picture of motion, then reminds us that coherence is not the same as completion. We end where we began, with the chair and the feeling of stillness. The chair is not stationary, it is a node in a moving, expanding cosmos, carried by layered motions that mostly cancel in sensation. The terror is not speed, it is that there is no privileged viewpoint from which speed becomes absolute. We can measure our drift against ancient photons, and we can map the nearby currents, but the last frame remains a definition, not a destination. The camera returns to the quiet room, and the sound design emphasizes the absence of wind, the absence of vibration, the absence of any clue. Motion is everywhere, and stillness persists anyway. In the end, still means agreed upon, not universally true. The room is quiet, the body is calm, and the universe is in motion anyway, an immense choreography, held together by laws we can test and bounded by horizons we cannot cross. Across this journey, we learned that stillness is not a measurement, it's a biological prediction built to keep you upright. Your inner ear flags acceleration, your brain subtracts steady signals, and a shared, smooth ride becomes invisible by design. Then we climb the stack of motion, one layer at a time, and each layer left fingerprints our senses ignore but our instruments cannot. Earth's rotation writes itself into Foucault's slow-turning line, into Coriolis curved winds, into an equatorial bulge mapped from orbit, even while the ground feels quiet. Beyond that, we found ourselves in free fall around the Sun at nearly 30 kilometers per second, with the seasons driven by tilt, not distance, and with aberration, parallax, and Doppler corrections proving the orbit in the sky's tiniest shifts. We followed that orbit as the Sun itself moved, circling the Milky Way inside a dark halo we infer from gravity, and we watched Gaia turn 1 billion star motions into a map of our local current. And when we widened the frame again, the galaxy became a boat in a river of galaxies, pulled by Virgo, by Laniakia's basin, and by the obscured mass we call the Great Attractor, where light, dust, and dark matter refuse to line up neatly. The deeper we looked, the more motion became a bookkeeping problem, separating Hubble expansion from peculiar drift, and separating real flows from the biases of distance ladders. Finally, we reached the closest thing cosmology offers to a baseline, the ancient microwave afterglow that fills all directions almost perfectly. In the frame where that 2.725 Kelvin C looks most uniform, our local speed is about 370 kilometers per second, a precise answer that still carries an unsettling caveat, because even that answer is not an anchor to absolute rest. It is a choice of reference, a practical convention tied to a 380,000-year-old snapshot of the universe. And at the edge of the map, where horizons limit what can ever be compared, the remaining questions, dark matter's nature, bulk flow debates, odd CMB alignments, and the slow drift of every fixed backdrop stay unresolved for a reason. They are reminders that our best cosmology is not a final still point. It is a disciplined way of describing motion without pretending the universe owes us a center. In other words, the terrifying reality isn't the speed itself, it's the discovery that stillness was never a universal state at all, only a local agreement held together by smoothness, gravity, and scale. We can measure our ride with astonishing precision, from millikelvin dipoles to microarc-second star shifts, yet the deeper truth is that every measurement is relative to something else that also moves. And that is the ending we earn. Not a single number that makes the fear go away, but a clearer view of what motionless has always meant and what it never could. The universe is not a stage we cross, it is the choreography itself, and we are inside the pattern whether we feel it or not. So why don't you notice while Earth spins, orbits, and drifts through larger currents at once? Because your body detects changes in motion, not constant velocity, and because rest in physics is only ever rest relative to a chosen frame. And what can we truly say we're moving relative to? We can name the frames we share, Earth's surface, the solar system barycenter, the local stars, and we can use the CMB as a cosmic yardstick, but we cannot point to an absolute final stillness behind them all. If there is one honest comfort in this, it is that you are not failing to feel the truth. You are feeling exactly what smooth shared motion feels like, nothing at all. The fear comes later, when you realize that nothing was never emptiness, it was agreement. Out there, every reference drifts, every backdrop slowly rearranges, and even the oldest light we can see only offers a frame, not a throne. Stillness is not where the universe is, it is what we call the moment our measurements stop fighting each other. If you want to keep going, follow the next measurement. Question the frame, check the residuals, and let the sky's smallest mismatches teach you what moving really means.